What are the chances that, within a mere 72 hours, two distant suns would detonate into naked-eye brilliance, two colossal earthquakes would rip across the Venezuelan crust, and the notorious Three-Eye Atlas would be brushed by a violent solar storm? On paper, this reads like the opening montage of a disaster blockbuster, a sequence any film editor would strike out as implausible. Yet it is not fiction. It is happening now, a reality staging one of the most synchronized celestial and terrestrial performances in living memory. In the wake of these events, even the most disciplined skeptics find themselves pausing, caught between the comfort of statistics and the vertigo of something that feels larger than chance. Tonight, we will peel back each occurrence with almost surgical care, tracing the science behind stellar convulsions and planetary upheavals, then push into the uneasy frontier where coincidence blurs into pattern. Stay with me as we journey through the story of September 2025, because what emerges from this investigation may unsettle our assumptions about what is truly unfolding above our heads. Part 1. An insane chain of events. Two stars erupt into brilliance, two massive earthquakes tear open the Venezuelan crust, and an interstellar traveler is struck by the breath of a coronal mass ejection, all within days of one another in late September 2025. If it feels as though the universe itself is staging a message, you are not alone in that impression. What follows is a mapping of this cosmic convergence with as much precision as we can muster. On September 23rd, astronomers recorded V1935 Centauri, a nova blossoming in the southern constellation of Centaurus, flaring to naked-eye magnitude at 5.8. Mere days later, another stellar detonation declared itself. V7994 Sagittari, brightening in the Archer constellation to magnitude 6.2. Two stellar outbursts, both suddenly visible to anyone willing to step outside and gaze skyward. Meanwhile, thousands of miles from the nearest telescope, the Earth itself answered with its own turbulence. At 2221 UTC, on September 24th, a magnitude 6.2 earthquake struck 24 kilometers east-northeast of Mena Grande in Venezuela's Zulia state. Its origin point, just 7.8 kilometers beneath the ground, sent tremors echoing through Venezuela and across into Colombia. Yet, nature had more to say. Hours later, at 0351 UTC on September 25th, another quake struck the same terrain, this time a magnitude 6.3 fracture at a depth of 14 kilometers. Twin stars, twin quakes, and above it all, invisible to human sight but traced by satellites, something even stranger was unfolding. Solar weather teams at NOAA's Space Weather Prediction Center tracked coronal mass ejections, titanic clouds of magnetized plasma flung from the sun at speeds surpassing 1,000,000 miles per hour. Their simulations suggested these solar tempests were on a collision course with something extraordinary. Three-Eye Atlas, the third interstellar object ever confirmed to visit our solar system. Here, the chronology takes on an almost theatrical quality. The nova eruptions, the Venezuelan earthquakes, the solar storm forecasts all clustered between September 23rd and 25th. During this same window, Three-Eye Atlas, discovered only 2 months earlier by the Asteroid Terrestrial Impact Last Alert System, was navigating the inner solar system amid one of the most turbulent phases of solar cycle 25. The scales of these events defy intuition. The novae ignited in Centaurus and Sagittarius, constellations visible from Earth's southern hemisphere, their light having journeyed for thousands of years to arrive in this week. The Venezuelan earthquakes ruptured near Mena Grande, in the tectonic frontier where the Caribbean and South American plates grind relentlessly together. The coronal mass ejection expanded through the inner heliosphere, a region of space that dwarfs Jupiter's orbit, and 3I Atlas itself. It was threading the ecliptic plane, weaving between Mars and the Sunday. We are not declaring a chain of causation that would be reckless. What we are doing is tracing the cluster, documenting the convergence, and weighing the rigor of mainstream scientific explanations against the pull of more adventurous interpretations. The U.S. Geological Survey recognizes no demonstrated tie between space weather and seismic activity. Solar physicists consider coronal mass ejections standard expressions of an active star. Astronomers see novae as inevitable outcomes of binary evolution. But what makes this week unique in the modern astronomical record is the presence of 3I Atlas, only the third interstellar object observed, following Oumuamua in 2017 and Borisov in 2019. More remarkable still, it is the first time we may observe such an interstellar wanderer endure the fury of solar storms near solar maximum. We know what solar tempests can do. In 2007, the European Space Agency's Stereo spacecraft filmed a coronal mass ejection ripping the ion tail from comet Encke, a brutal reminder of how space weather reshapes fragile bodies. The implications for the months ahead stretch far beyond academic curiosity. On October 3rd, 3I Atlas makes its close pass by Mars, sweeping within 0.19 astronomical units, about 28 million kilometers of the red planet. Orbiting spacecraft, from ESA's ExoMars to NASA's Mars Reconnaissance Orbiter, are primed to capture opportunistic images that could reveal the structure of the visitor's nucleus and coma in unprecedented detail. By October 29th, 3I Atlas will reach perihelion, its closest approach to the Sun at 1.36 astronomical units, still outside Earth's orbit, but near enough for ground-based telescopes to scrutinize its behavior in real time. The geometry improves further on December 19th, when the object makes its closest approach to Earth at 1.8 astronomical units. For perspective, that is closer than Mars at its farthest, giving professionals and amateurs alike months of observing opportunity. And all of this is unfolding during a season when space weather tends to intensify. The autumn equinox enhances what space physicists call the Russell-McFerran effect, a geometric twist in Earth's magnetic field that amplifies its interaction with solar wind. September through November have long delivered the most dramatic auroras and the strongest solar-induced disruptions. Our commitment is simple. We will offer both measured scientific explanations and imaginative what-if scenarios, each clearly labeled. You deserve to know what is confirmed, what is speculative, and what is pure conjecture. The data matters, the wonder matters, and sometimes the most truthful thing science can admit is this: we do not yet know, but we are watching. So hold this question in your mind as we continue. If coronal mass ejections can sever the tails of comets that have circled our sun for eons, what might they do to a body forged in another stellar nursery, carrying dust and ice across millions of years of interstellar darkness? We are about to find out. Next, we turn our attention to those twin stellar eruptions, the novae that lit the southern skies just as Earth's crust began to tremble. Part 2. The two novae. Sudden southern sky explosions. In the pre-dawn hours of September 23, 2025, amateur astronomer John Seitch was following a ritual he had honed for decades, sweeping the southern skies from his observatory on Chatsworth Island, New South Wales, watching for the sudden appearance of stellar fire. That morning, his patience was rewarded. What he recorded would soon set off alarms on gamma-ray satellites and turn the gaze of orbiting X-ray telescopes toward a patch of sky in Centaurus. The star V1935 Centauri announced itself not with sound or spectacle, but with light. Sitch's initial photographs revealed a point where no star had ever appeared bright enough to stand out before. At magnitude 5.8, the nova was faint, but still within reach of sharp human vision under pristine, dark skies, just bright enough for anyone willing to step outside and look. But this was no ordinary brightening. Within hours of Sitch's report reaching the Central Bureau for Astronomical Telegrams, space-based observatories began registering something remarkable. NASA's Fermi Gamma Ray Space Telescope lit up with signals from high-energy photons racing in from Centaurus. Almost simultaneously, the Swift Observatory, a satellite built to track fleeting bursts of gamma radiation, pivoted its instruments and began capturing hard X-ray emission. What Swift saw confirmed the violence of the nova's expanding shockwave. The data spoke of physics operating at the limits. Electrons and protons whipped to nearly the speed of light, magnetic fields tangled into turbulent knots, and temperatures soaring into the millions of degrees. For backyard stargazers, this was a spark of wonder. For astrophysicists, it was a laboratory in the sky, a chance to watch matter pushed into extremes normally reserved for supernova remnants or the engines of distant galaxies. And the universe was not done. Just days later, the sky erupted again. This time it was V7994 Sagittarii, blazing to life in the neighboring constellation of the Archer. It reached magnitude 6.2 at discovery, too dim for casual naked-eye viewing, but easily visible with small binoculars or a modest telescope. Two novas, both credited to the same watchful observer, both flaring within the same week, an astronomical coincidence that immediately caught the attention of professionals worldwide. Novae are not rare in themselves. Astronomers expect a dozen or so each year scattered across the Milky Way. But two rising almost to naked-eye brightness within days of one another is rare enough to draw comparisons with historic seasons of activity. The last time observers enjoyed a similar double display was in the summer of 2023. Before that, one must look back several years. The sheer timing elevated these discoveries from ordinary transients to celestial events of genuine note. The physics behind a nova is a slow-burn drama of stellar cannibalism played out over centuries. At its heart lies a white dwarf, the super-dense core left behind when a sun-like star dies. Roughly Earth-sized but carrying a mass comparable to our own star, this remnant orbits a living stellar companion, stealing hydrogen from its outer atmosphere. Over decades, centuries, even millennia, gas trickles onto the white dwarf's surface, compressing under gravity until temperature and pressure reach ignition. In a flash, the accumulated hydrogen ignites in runaway thermonuclear fusion. Unlike the steady, balanced fusion of living stars, this is an uncontrolled detonation, brightening the system by factors of 10,000 or more. The explosion blasts away the surface layer, but spares the white dwarf itself, which resumes its slow theft of hydrogen until the cycle repeats. Some such systems erupt every few decades. Others may sleep for millennia between outbursts. What made V1935 Centauri exceptional was not merely its visibility, but the signature of high-energy physics it unleashed. When its detonation hurled matter outward at thousands of kilometers per second, shock fronts formed that accelerated particles to relativistic speeds. Those particles collided with magnetic fields and surrounding gas, emitting the gamma rays and hard X-rays that triggered Fermi and Swift. It was the same violent machinery known from supernova shells and quasars. Compact particle accelerators scattered across the universe, suddenly mirrored in our galactic backyard. For sky watchers in the southern hemisphere, both novae appeared in favorable positions. V1935 935 Centauri lies well south of the celestial equator, making it a challenge for northern observers but a prime target for those south of the equator. V7994 Sagittarii, in the Archer constellation, followed a similar pattern low in the southern sky for mid-northern latitudes, yet nearly overhead for observers in Australia, South America, and Africa. The discoveries also highlighted the collaborative fabric of modern transient astronomy. Sitch's report, submitted through the International Astronomical Union's Central Bureau for Astronomical Telegrams, triggered a rapid chain of follow-ups. Circular number 5611 confirmed the detection of V1935 Centauri. Soon after, Circular 5612 documented V7994 Sagittarii. What began as one amateur's disciplined watch quickly became a global scientific campaign, linking backyards, professional observatories, and spaceborne instruments in the common pursuit of understanding how dead stars flare back to life. Within days of discovery, observatories across the globe turned their instruments toward the new stars, measuring their light with precision. Photometry revealed the exact changes in brightness, while spectroscopy laid bare the fingerprints of hydrogen, helium, and heavier elements expanding outward in the nova shells. The story of these eruptions is not told by professionals alone. Amateur astronomers, coordinated through groups like the American Association of Variable Star Observers, provide the heartbeat of nova science. Their nightly vigilance creates a time-lapse of light curves, tracing the rise, plateau, and gradual fading that encode the physics of the explosion and the secrets of the binary systems behind them. Large telescopes cannot afford to watch every nova without pause, but amateurs can, logging changes night after night. Their collective labor threads together the raw chronicle of how these stellar outbursts live and fade. Even the names carry stories. V1935 Centauri became the 1935th officially catalogued variable star in Centaurus, while V7994 Sagittarii entered the books as the 7994th in Sagittarius. To newcomers, the numbering can appear bewildering, since official designations often replace temporary discovery tags, and administrative lags sometimes assign lower numbers to later finds. Still, the permanence of these labels ensures their place in astronomical memory. Both novae will fade over weeks to months, perhaps years, following the long decline typical of such events. Yet the arc is not always smooth. Some novae produce dust weeks after eruption, dimming as newly minted grains scatter the light. Others flicker with multiple peaks, their curves shaped by competing physical processes. Each one writes its own narrative of how stars recycle matter back into the galaxy. The timing, however, sparked whispers beyond the data. Two novae blazing forth during a week of severe geomagnetic storms, alongside twin earthquakes in Venezuela, and the passage of an interstellar wanderer through the inner solar system, the juxtaposition seemed uncanny. Astronomers affirm novae in distant constellations pose no threat to Earth, no link to quakes or storms. Their titanic energies, though vast, are softened by the expanse of space, reaching us only as a gentle influx of photons, wondrous yet harmless. And still, the synchronicity stirs reflection. Sometimes, the cosmos aligns events with a rhythm that feels almost deliberate, stretching coincidence into something like poetry. Part 3. The Venezuela Quakes. At precisely 22 hours, 21 minutes, and 55 seconds, Coordinated Universal Time on September 24th, 2025, the crust of our planet convulsed beneath Venezuela's Zulia state, releasing an energy load comparable to several nuclear detonations. The shock registered as a magnitude 6.2 earthquake, its origin point lying just 24 kilometers northeast of Mena Grande. At a depth of only 8 kilometers, the rupture was shallow, close enough to the surface to unleash destructive shaking across two nations. Seismic waves radiated outward at nearly 6 kilometers per second, racing through rock and soil, arriving in nearby towns within moments of the fracture. From Maracaibo's crowded streets to the avenues of Caracas, from villages along the Colombian border to settlements dotting the Caribbean coast, millions of people felt the ground sway and buckle beneath them. Within minutes, social media brimmed with clips of chandeliers swaying like pendulums, windows clattering against their frames, and residents fleeing into the night as emergency protocols snapped into place. But the Earth was not finished. Just 5.5 hours later, at 03 hours, 51 minutes, and 39 seconds UTC on September 25th, the crust lurched again. This second rupture, a magnitude 6.3 event, struck almost the same location. Though originating from a slightly greater depth of 14 kilometers, still shallow by seismological standards, it was powerful enough to rattle the surface violently. Its epicenter lay 27 to 28 kilometers northeast of Mena Grande, overlapping the earlier rupture zone as if the Earth itself were tearing along the same scar. To appreciate the significance of these twin shocks, one must recall the logarithmic nature of earthquake magnitudes. A magnitude 6.3 earthquake does not merely exceed a 6.2 by a fraction, it releases nearly twice the energy. Taken together, the double rupture represented a release equivalent to a single magnitude 6.4 to 6.5 event, a seismic outburst notable even in a global context. Indeed, these Venezuelan earthquakes ranked among the most significant quakes of late September 2025, alongside the magnitude 7.8 Kamchatka event that had rattled the Pacific just days before. Aftershocks soon followed. Later on, September 25th, a magnitude 5.8 tremor reverberated through the same fault zone, part of the natural decay pattern known to seismologists as the Omori sequence. Though smaller in magnitude, a 5.8 quake is still strong enough to inflict damage, especially on already weakened structures, and to sustain the anxiety of residents enduring sleepless nights. Regional tectonics explain why this corner of South America is prone to such upheaval. The Maracaibo Basin straddles a geologically complex frontier where the Caribbean plate grinds relentlessly against the South American plate. The collision manifests in a web of active fault systems, including the Boconó fault system and the Oca-Ancon-Santa Marta trends. These geological seams accumulate stress for years, decades, even centuries, until finally the locked rock breaks free in sudden slip events. That energy release is what humans experience as an earthquake. The disparity in depths between the twin main shocks mattered greatly for the human experience of shaking. Shallow quakes, like the 7.8-kilometer rupture on September 24th, tend to deliver stronger accelerations at the surface because the seismic waves have less distance in which to dissipate. This explains the widespread reports of intense shaking across western Venezuela and into Colombia during the first event. The second, deeper rupture at 14 kilometers, while comparable in magnitude, was filtered slightly more by the overlying crust, though still potent enough to cause alarm. Different monitoring agencies reported subtly different figures for these events. The United States Geological Survey initially listed the September 24th quake as magnitude 6.2, while the European Mediterranean Seismological Center and other networks offered ranges between 6.1 and 6.3. Such discrepancies are common and reflect both the complexity of measurement and the evolving nature of seismic analysis. As additional data streams in from worldwide seismic stations, values are updated, distinctions drawn between moment magnitude, surface wave magnitude, and body wave magnitude. Yet beyond the statistics lies the human story. Thousands evacuated multi-story apartments swaying precariously during the tremors. Emergency response teams fanned across Zulia State, inspecting bridges, hospitals, and power facilities to ensure their continued operation. Though initial reports suggested limited structural collapse relative to the quake's size, survey teams pressed on for days, searching for hidden cracks, subtle displacements, and the slow injuries earthquakes leave behind in concrete and steel. For the people of Venezuela and Colombia, these twin quakes were not just numbers on a seismogram, but lived moments of fear, resilience, and the uneasy reminder that the ground beneath them is never entirely still. The tectonic mosaic surrounding Lake Maracaibo and along the broader boundary where the Caribbean plate grinds against South America is a restless one. Earthquakes occur there with regularity, though shocks of the size witnessed in September 2025 erupt only sporadically. The geological record shows that major ruptures in this corridor can sometimes awaken neighboring faults, a process seismologists call stress transfer when one quake alters the pressure landscape, shifting the load onto adjacent segments and priming them for failure. This possibility hung in the air in the hours and days following the twin Venezuelan quakes. Could another large rupture follow? The statistical answer is cautious. Aftershocks are expected, and indeed inevitable, their frequency and strength decaying over time. The largest typically strike within days or weeks of the main shock. Yet whether an even greater quake might follow is a question science cannot presently answer with confidence. Despite decades of searching for reliable precursors, from subtle shifts in ground deformation to strange patterns in radon emissions or electromagnetic signals, earthquake prediction remains one of geophysics' most elusive goals. As the ground continued to stir, international seismic networks tracked every tremor. Each aftershock was logged, catalogued, and analyzed, helping researchers piece together a portrait of how the regional fault system was redistributing stress. The Global Centroid Moment Tensor project began publishing detailed models of the fault orientations, slip directions, and rupture mechanisms of the two main shocks. These data revealed not only which specific faults had broken, but also how the strain map of northwestern Venezuela had been rewritten in the span of hours. For the people of Zulia State and its neighbors, the statistics and fault plane solutions mattered less than the lived reality. The earthquakes were visceral reminders that their land rests upon a tectonic battlefield. Building codes, emergency drills, and community preparedness were tested in real time. The fact that damage was moderate relative to the earthquake's magnitudes likely owed much to circumstance. The quakes struck at hours when many were at home, rather than inside vulnerable offices or schools. Improved construction standards and increasingly coordinated emergency responses also played roles in limiting casualties and collapse. Yet beyond the seismology, a broader question echoed in public imagination. Why did all of this happen during a week already dense with cosmic drama? Two novas erupted in southern skies. An interstellar object threaded the solar system. The sun itself seethed with storms, and the Earth's crust convulsed, all within days. Professional seismologists remain firm. There is no verified physical mechanism linking solar flares, geomagnetic disturbances, or astronomical events with tectonic ruptures. The U.S. Geological Survey underscores that correlations proposed over the years remain unproven, no matter how compelling they may appear in hindsight. Still, the human instinct for pattern-seeking is irrepressible. Clusters of extraordinary events feel meaningful, even if causation lies beyond our grasp. Perhaps the most honest scientific stance is to document the sequence, analyze each phenomenon on its own terms, and remain open to surprises, resisting the urge to weave causality from coincidence. As Venezuelans endured the aftershocks, another reminder loomed on the horizon. The sun itself was preparing to show that the dynamic theater of Earth is mirrored in the restless drama of space. Part 4: The Sun Fires. 93 million miles above Venezuela's trembling ground, our star was staging its own explosive performance. In the very days when novae lit southern skies and twin earthquakes ruptured the bedrock of South America, the sun was busy hurling coronal mass ejections into the void, billion-ton avalanches of magnetized plasma, and this time their path crossed something utterly new in the history of human observation: an interstellar traveler. Coronal mass ejections, or CMEs, rank among the most violent phenomena our solar system can produce. They begin in the corona, the sun's tenuous outer atmosphere, where magnetic field lines twist and buckle like overstretched wires. When reconnection occurs, a sudden reconfiguration of the field, the release of energy rivals billions of hydrogen bombs. Plasma is flung outward at speeds from 250 to 3,000 kilometers per second, fast enough to cover the Earth, sun distance in a handful of days. NASA's Space Weather Prediction Center models these storms using WSANLL, a numerical simulation that charts how such eruptions expand through the heliosphere. The model accounts for solar wind density, velocity, and magnetic polarity to forecast which planets, spacecraft, or passing bodies will find themselves in the firing line. By late September 2025, Enlil runs revealed a roiling inner solar system. Multiple CMEs were threading across the ecliptic during the very window that gave us twin stellar eruptions and Venezuela's double quake. But this time, the solar ballet had a partner without precedent. For the first time in recorded history, one of these plasma storms appeared to be on a collision course with an object born beneath another star. That object was 3I Atlas, the third confirmed interstellar visitor after Oumuamua in 2017 and Borisov in 2019. Detected only 2 months earlier by the Asteroid Terrestrial Impact Last Alert System, it was moving along a retrograde path inclined nearly 175 degrees to the ecliptic plane, a trajectory that plunged it directly through regions most frequently swept by solar weather. The geometry was extraordinary, an alien body from beyond our system meeting the sun not under calm conditions, but during one of solar cycle 25's most active phases. We have precedent for what such encounters look like. In 2007, the European Space Agency's Stereo spacecraft recorded a CME slicing clean through the ion tail of Comet Encke. The disconnection event lasted hours, a brutal reminder that solar storms can literally rip part of a comet away. The physics is well understood. Comets grow 2 kinds of tails: dust tails, gently arcing away under the push of sunlight, and ion tails, rigid streamers of charged particles pulled along magnetic field lines in the solar wind. When a CME arrives, magnetic reconnection can sever those lines. The ion tail detaches, drifts into space, and dissipates, while a new tail gradually grows from fresh material. The claim that 3I Atlas was sideswiped by such a storm rests primarily on trajectory modeling rather than direct imagery. Enlil forecasts indicated overlap between CME paths and the interstellar traveler's position in late September, but uncertainties remain. Space weather models are superb at capturing broad dynamics, less so at the fine scale of individual encounters. Thus, any assertion must be framed as inference, not proof. If the interaction occurred, astronomers know what signs to seek. The coma, the diffuse envelope of gas and dust surrounding the nucleus, could brighten as increased ionization drove fresh material outward. The morphology of the ion tail might shift or fragment, betraying magnetic disturbances. Spectra might reveal sudden releases of molecules such as CN, CO, or CO2 from the object's ice, energized by the storm. Around the world, networks of amateur astronomers stood ready. Their telescopes, though modest compared to professional observatories, can capture nightly sequences of images. When stitched together, those mosaics reveal subtle changes in brightness and structure that larger facilities, occupied with scheduled programs, often miss. At the heart of these interactions lies elegant but unforgiving physics. When magnetized plasma strikes a cometary ionosphere, magnetic field lines connect and snap apart, releasing stored energy and accelerating particles. The same reconnection that powers solar flares and geomagnetic storms on Earth plays out again. This time upon a body forged around another Sunday. Watching such processes in real time, on material that formed billions of years ago in an alien system, is to witness astrophysics at its rawest and most universal. 3. Atlas is more than a cometary curiosity. It is a messenger from another stellar nursery, carrying within its ices and dust a record of environments our solar system never knew. To see it interact with our sun, to watch the clash of alien material with familiar solar violence, is to glimpse how cosmic weather shapes not only our home system, but the larger galaxy itself. The stage is set, the actors aligned, the sun in eruption, the interstellar visitor crossing the stage, and humanity watching, waiting, documenting what unfolds when worlds and stars collide. If solar storms are indeed altering the behavior of this object, then we are witnessing the first documented instance of our sun directly shaping matter from another stellar neighborhood. The geometry of this encounter makes it more favorable than anything we have seen before. Unlike Oumuamua, which swept through the inner solar system at high speed and along a steep inclination to the ecliptic, 3I Atlas traces a course that hugs the ecliptic plane itself, the same celestial stage where the sun channels most of its storms and where Earth endures the brunt of space weather. By traveling through this busy corridor, the interstellar visitor has placed itself in harm's way, within reach of the sun's temperamental moods. Solar Cycle 25 provided the backdrop, and it has been an especially turbulent one. The cycle, which entered its maximum in 2024 and 2025, has unleashed higher sunspot counts, more frequent flares, and an elevated rate of coronal mass ejections. By sheer timing, 3I Atlas is experiencing our star at its most volatile, enduring the kinds of conditions that Oumuamua and Borisov bypassed. It is as though the universe has staged a laboratory experiment, handing us a sample from another system and exposing it to the sun's storms at full intensity. Observational confirmation of such interactions demands patience and rigor. Astronomers must look for subtle signs, changes in brightness measured night by night, spectral fingerprints revealing freshly released molecules, or alterations in the structure of its coma and tail unfolding across hours and days. Both professional observatories and dedicated amateurs turned their instruments toward 3I Atlas through late September, building a global archive of data. Yet initial results remained tentative, with analysis still underway as the weeks closed. The implications reach far beyond a single object. To witness how our sun shapes interstellar material is to glimpse processes likely happening across the galaxy. Every star produces its own tempests, its own coronal mass ejections, and wandering interstellar fragments surely pass through those storms as well. 3I Atlas may even bear scars of such encounters, signatures etched during its million-year odyssey across multiple stellar neighborhoods before arriving here. Each interaction leaves traces, like weathering on a stone carried down a river, telling stories of places long departed. As September 2025 drew to an end, the calendar itself seemed to compress into a chapter of cosmic drama. Stellar explosions lighting southern skies, earthquakes rattling the crust of South America, solar storms surging across space, and an interstellar messenger threading through it all. Were these simply unrelated phenomena clustering in time, or was there some deeper rhythm beneath the surface? For now, the most honest stance was to keep watch, to follow the evidence, and to let the visitor's journey speak for itself. Ahead lay a close approach to Mars on October 3rd, an encounter that promised fresh opportunities to see whether the sun's storms had truly left their mark on this traveler from beyond the stars. Part 5. Weirdness Framed. Step back for a moment and consider the map we've been drawing. Two stellar eruptions suddenly visible to the naked eye, two earthquakes of magnitude 6 striking within hours of one another, coronal mass ejections threading across the inner solar system, and, woven through it all, an interstellar visitor crossing our neighborhood at the very height of solar maximum. It is a lot of universe compressed into a very small span of time, the final week of September 2025, dense with cosmic theater. This is the uneasy boundary where honest science collides with human pattern recognition. Our minds evolved to search for significance in complexity. The rustle in tall grass might have meant a predator, a shifting cloud bank might have heralded rain, a subtle change in someone's expression could have revealed danger or opportunity. That same cognitive architecture helps us survive, but it also predisposes us to find meaning in coincidence. When dramatic events cluster, the instinct is to believe they must be linked. The scientific mainstream speaks clearly here. The United States Geological Survey maintains that no proven connection exists between solar storms and seismic ruptures. Decades of correlation studies have found no predictive relationship between sunspot counts, solar flares, geomagnetic disturbances, and earthquakes. Seismologists emphasize that earthquake prediction remains beyond our grasp, whether one searches for terrestrial warning signs or for extraterrestrial triggers. Similarly, stellar astronomers treat novae as well-understood outcomes of binary star evolution. White dwarfs steadily accrete matter from their companions until the pressure ignites runaway fusion on their surfaces. The eruptions are spectacular, but they are normal, the natural punctuation marks of stellar life cycles. V1935 Centauri and V7994 Sagittari, however dramatic to the eye, fit squarely into this framework. Solar physicists view coronal mass ejections the same way. These eruptions are consequences of tangled magnetic fields unwinding in the sun's corona, expected to occur more often during maximum phases of the 11-year solar cycle. Late 2025 is statistically ripe for such storms. And comet CME interactions are not mysteries. Spacecraft have filmed them directly, recording the disconnection of ion tails as magnetic reconnection rearranges charged particles. Plasma physics, not exotic forces, explains what we see. Yet acknowledging mainstream explanations need not strip away wonder. Sometimes events align in ways that stretch coincidence toward what feels like synchronicity. To hold both truths, rigorous skepticism, and appropriate awe, is part of the scientific enterprise. Our approach in this investigation will keep boundaries clear. At the base are observations, magnitudes, coordinates, spectra, times stamped into seismographs and telescope logs. On that base stand interpretations rooted in tested physics and models. Beyond that lies speculation, the territory where we explore connections not yet proven, mechanisms only hypothesized, and possibilities that might one day earn evidence. Speculation is welcome, provided it is labeled honestly as such. For clarity, we pause to define our vocabulary. A nova is a thermonuclear explosion on the surface of a white dwarf, brightening its system by factors of thousands, but leaving the star intact. A supernova, in contrast, destroys the star entirely. A coronal mass ejection is a billion-ton surge of plasma launched into space at hundreds to thousands of kilometers per second. Perihelion is the closest orbital point to the Sun's. One astronomical unit equals the Earth-Sun distance, about 93 million miles, or 150 million kilometers. Ion tails, carved from cometary gas by the solar wind, stretch millions of kilometers and align with the invisible magnetic field lines flowing outward from the Sun. They are banners of plasma physics, visible threads of an otherwise invisible force. In the weeks ahead, our path is clear. We will examine the detailed mechanics of stellar explosions, trace the dynamics of seismic ruptures, and map the choreography of solar storms. We will follow 3I Atlas through its October 3rd flyby of Mars and its October 29th perihelion, watching for signs of how solar tempests may shape its ancient surface. Alongside rigorous physics, we will also allow space for questions that tread beyond the boundaries of proven science. The equinox season itself plays its role, amplifying space weather through the Russell-McFerran effect, that peculiar alignment of Earth's magnetic field and solar wind that so often intensifies auroras and geomagnetic storms in September and October. What unfolds will test not just our instruments, but our willingness to embrace both evidence and wonder as the universe arranges its events in a sequence that feels almost too precise to ignore. This seasonal enhancement of geomagnetic activity helps explain why late September often yields heightened space weather without invoking any connection to earthquakes or stellar events. Against this backdrop, 3I Atlas stands out as a once-in-a-generation opportunity. It is only the third interstellar visitor ever confirmed, and the first to be observed under the volatile conditions of a solar maximum. Its trajectory lies close to the ecliptic plane, the crowded stage where planets, asteroids, and most solar storms perform. That geometry maximizes both the likelihood of interaction with space weather and the chances for multiple spacecraft to capture its passage. Oumuamua raced through the solar system too quickly for thorough study. Borisov lingered longer, but at a distance that blunted many of our instruments. By contrast, 3I Atlas grants months of close scrutiny. October and November promise critical moments, and the stakes extend far beyond curiosity. During the October 3rd flyby, Mars Orbiter missions, ESA's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter have scheduled opportunistic observations. If successful, these could provide the sharpest images ever taken of an interstellar visitor's nucleus and the diffuse structure of its coma. Meanwhile, ground-based telescopes across the globe remain locked on target, measuring subtle shifts in brightness, spectral fingerprints of liberated molecules, and tail morphologies that may betray the fingerprints of solar storms. On Earth, another watch continues. In Venezuela, seismologists track aftershocks expected to rattle on for weeks or months after the twin ruptures of September. While the science cannot predict whether a larger quake lies ahead, continuous monitoring records every vibration, mapping the redistribution of stress along the tangled frontier between the Caribbean and South American plates. This tectonic complexity guarantees more earthquakes in the future, though their timing will always remain uncertain. Our responsibility, in navigating such convergences, is clarity. Mainstream science provides the foundation, explanations rooted in established physics and supported by decades of observation. Yet speculation deserves space too, so long as it is marked honestly as hypothesis, not fact. And human intuition, our impulse to find meaning in clustering events, deserves acknowledgement, even when the evidence points toward coincidence. Perhaps the most striking element of this convergence is its timing within human history. We are the first generation capable of tracing interstellar objects across the solar system, of watching stellar explosions across the electromagnetic spectrum, of measuring earthquakes worldwide in real time, and of modeling solar storms as they sweep through space. Past generations could witness novae with the naked eye or endure earthquakes beneath their feet, but they lacked the technology to see these events as part of a larger, interconnected tapestry. Here, then, is our guiding principle: to separate what is observed from what is imagined, what is proven from what is merely possible, what is likely from what is conceivable. And as we move deeper into this story, one question rises naturally. How does a star explode so violently, yet survive intact, resuming its quiet rhythm after the flash? The answer lies in physics operating on scales so vast they strain human intuition, a stage where the cosmos rehearses destruction without finality, allowing light to bloom without obliteration. Part 6. Anatomy of a nova. Picture, if you will, a star no larger than Earth, yet holding the mass of our Sunday. This is a white dwarf, the skeletal remnant of a once-living star. On its surface, gravity crushes matter until densities approach 1,000,000 times that of water. Temperatures linger near 50,000 degrees Fahrenheit, hot enough to make iron glow white. What remains is a corpse of degenerate matter, where atoms are pressed into quantum states no laboratory on Earth could reproduce. Now imagine this remnant locked in orbit with a still living partner, perhaps a red giant that has swollen with age, its outer atmosphere stretched thin and vulnerable. The white dwarf pulls at that atmosphere with unrelenting gravity, stealing hydrogen gas in steady streams. The material spirals inward like water circling a drain, finally landing on the dwarf's surface. There it builds up, layer upon layer, compressed under almost unimaginable pressure. For decades, centuries, even millennia, this invisible burden grows. Then, one day, the balance tips. When temperatures climb to roughly 100 million degrees Kelvin, hydrogen ignites not in steady fusion, but in runaway reaction. In seconds, a thermonuclear explosion consumes the stolen layer. The nova V1935 Centauri was born in just such a moment, a detonation releasing energy equal to thousands of years of our sun's output. Unlike a supernova, this cataclysm spares the white dwarf itself. The eruption blows away only the accumulated skin of gas, leaving the core intact, ready to repeat the cycle again. This violence is what drew the attention of space-based observatories. When NASA's Fermi Gamma Ray Space Telescope registered high-energy photons from Centaurus, it was recording particles whipped to near-light speed in the nova's shock fronts. Swift's detections of hard X-rays traced electrons spiraling through magnetic fields, radiating synchrotron energy across the spectrum. What might seem like a bright point in the sky is, in truth, a natural particle accelerator, an engine hurling matter to energies that Earth-bound cyclotrons struggle to reach. The nova's ejector, racing outward at thousands of kilometers per second, slam into interstellar gas, creating shock waves that act like cosmic turbines for protons and electrons alike. Amateurs contribute their own lens on this drama. Through the American Association of Variable Star Observers, they measure brightness night after night, sometimes by eye, sometimes with CCD cameras. These continuous records produce light curves that professionals cannot replicate, capturing subtle rises, plateaus, and declines. V1935, Centauri's curve, followed a familiar arc, a rapid climb from invisibility to naked-eye brightness, a peak that may last days or weeks depending on white dwarf mass and accretion rate, then a decline stretching over months or years. Some novae flicker with secondary peaks, signaling changes in the physics of their cooling shells. Spectroscopy adds further dimension. Early spectra reveal broad hydrogen and helium lines, broadened by the staggering velocities of the ejecta. With time, those lines narrow as material slows and cools. Later still, forbidden transitions appear, signatures that can occur only in thin, rarefied gas, where atoms may wait hours between collisions. Through these spectral fingerprints, astronomers reconstruct the nova's evolution in exquisite detail. The true distances to V1935 Centauri and V7994 Sagittarii remain uncertain, though likely spans several thousand light-years. Yet even across such gulfs, their explosions carry enough power to reach our telescopes reminders that stellar corpses, far from silent, can blaze back to life in eruptions that blend death and rebirth into the same event. What we saw in September 2025 were not events of the present, but echoes from the deep past. The twin explosions in Centaurus and Sagittarius actually occurred thousands of years ago, at a time when human civilization was only beginning to plant crops and settle into permanent villages. Their light has been crossing interstellar space longer than all of recorded history, arriving in our skies precisely during this extraordinary week, as though the cosmos had chosen its timing with theatrical precision. The marvel is that anyone, even without professional equipment, can join in observing. A digital camera fitted with a telephoto lens is sufficient to capture both novae at their peak brightness. With nothing more than binoculars or a small backyard telescope, observers can estimate their magnitudes by comparing them to neighboring stars of known brightness. More advanced amateurs, armed with CCD cameras and photometric filters, contribute even finer precision. Their nightly measurements create a continuous record of the light curves, supplementing professional data with temporal coverage that large observatories cannot always maintain. The names of these novae carry their own story, steeped in astronomical tradition. 1935 Centauri received its designation as the 1935 variable star officially catalogued in the constellation Centaurus. The V prefix signals variability, a reminder that its brightness waxes and wanes. This permanent designation replaces the temporary discovery tag's labels that might reference the discoverer's surname, the date, or a survey catalog number, and ensures that the nova has a place in the permanent ledger of stellar behavior. One of the most fascinating phases in nova evolution involves dust. Weeks to months after the eruption, certain novae experience a sudden dimming. As the ejected gas cools, microscopic dust grains condense, absorbing and scattering light. These dust dips can drop brightness by several magnitudes, masking the nova for weeks. Over time, the grains are either dispersed into interstellar space or destroyed by the nova's continued radiation, allowing the stellar remnant to shine through once more. The scale of energy involved dwarfs anything human. A typical nova unleashes energy equivalent to the sun's output over 10,000 years, enough to sustain human civilization for billions of years at current consumption. And yet, compared to a supernova, this is modest. Supernovae release so much energy that they can outshine entire galaxies for weeks, turning night into false day across cosmic distances. Not all novae erupt just once. Some are recurrent, detonating every few decades. These repeaters may erupt dozens of times over astronomical history, each event carrying the white dwarf a step closer to the Chandrasekhar limit. If that threshold is ever reached, the star will no longer survive. Its final act will be a Type Ia supernova, obliterating the dwarf itself. Professional follow-up of the September novae continues across the spectrum. Ground-based telescopes track optical brightness and spectral evolution. The Hubble Space Telescope may provide high-resolution images of the expanding shells of debris. Radio arrays listen for synchrotron emission, radiation from particles accelerated to relativistic speeds in the blast wave. Classification of both V1000, 935 Centauri, and V7000, 994 Sagittari, as classical novae rests securely on these patterns of spectral fingerprints and brightness evolution. They are not outliers, but textbook examples, stellar corpses that flare back to life, writing their ancient messages in the language of light across the canvas of the sky. Dwarf novae, driven by instabilities in accretion disks rather than full thermonuclear detonations, usually reveal themselves with different spectra and smaller brightenings. Luminous red novae, thought to result from stellar mergers, evolve in different colors and over different timescales. Could either of the September 2025 novae belong to one of these exotic categories rather than the familiar thermonuclear kind? For now, the evidence says no. Current observations remain consistent with classical nova physics. Yet astronomy, by its nature, keeps a healthy skepticism. Early classifications are provisional, and as more data pours in from across the electromagnetic spectrum, subtleties may emerge that refine our understanding. What already distinguishes V1000, 935 Centauri is its gamma-ray detection. That single discovery places it among a small but growing class of gamma-ray novae eruptions that defy traditional expectations by producing high-energy emissions normally associated with more violent astrophysical engines. These signals suggest particle acceleration far more efficient than once thought possible in nova environment. The physics may involve tangled magnetic fields snapping and reconnecting, shocks accelerating particles to relativistic speeds, or some hybrid of both mechanisms that link novae to the same processes driving supernova remnants and other cosmic accelerators. As astronomers traced these stellar eruptions across light, X-rays, and gamma rays, the ground beneath Venezuela reminded us that Earth, too, can rival the dynamism of distant stars. Beneath Lake Maracaibo and across Zulia State lies one of South America's most tectonically intricate crossroads. Here, the Caribbean plate grinds against the South American plate, creating a fault network as complex as it is restless. The Bocono Fault slicing northeast through the Venezuelan Andes, the Oca-Ancon Trend stretching along the Caribbean coast, and the Santa Marta Fault reaching into Colombia. For decades, even centuries, these boundaries have been stockpiling stress, energy biding its time until sudden slip would break the silence. At 22 hours, 21 minutes and 55 seconds UTC on September 24th, the silence ended. A magnitude 6.2 earthquake ruptured a fault segment about 7.8 kilometers underground. The shallowness of the rupture ensured that seismic waves retained their ferocity as they reached the surface, accelerating the ground with brutal force across two nations. The fault plane may have slipped by meters, its rupture extending several kilometers, a violent unburdening of stress accumulated over years. Seismic waves fanned outward at 6 kilometers per second. The first to arrive were P waves, compressional ripples pushing rock back and forth in line with their travel. They were followed by S waves, transverse oscillations that racked the ground side to side, delivering the kind of motion that topples walls and buckles infrastructure. Finally came the slower, rolling surface waves, often the most destructive of all, producing the long undulations that eyewitnesses described as lasting minutes. Then, before recovery could begin, the Earth struck again. At 3 hours 51 minutes and 39 seconds, UTC on September 25th, only 5.5 hours later, a second rupture shook the same region. This one, magnitude 6.3, came from a depth of 14 kilometers deeper than the first, yet still shallow enough to drive intense shaking. The culprit was likely a neighboring fault segment, its failure triggered by stress redistributed from the earlier rupture. This is the physics of stress transfer. When one fault slips, it alters the stress field nearby. Some zones are relieved, temporarily stabilized. Others are loaded, brought closer to the breaking point. On September 24th, the initial rupture appears to have primed the segment that failed hours later, and though the difference between 6.2 and 6.3 might sound marginal, the logarithmic scale conceals the truth. The second quake released roughly twice as much energy as the first. Together, they equaled the power of a single magnitude 6.4, 6.5 event, a seismic doublet ranking among the largest quakes worldwide that month. Different seismological agencies returned slightly varied numbers, a reflection of how difficult earthquake measurement truly is. The United States Geological Survey employs moment magnitude, based on the total energy released by the rupture, while others use methods emphasizing surface or body waves. The discrepancies are not contradictions but refinements, each dataset sharpening the picture of how Earth tore itself open beneath Venezuela in that charged week of September 2025. When the first headlines appeared, the reported magnitudes varied. Some listed 6.1, others 6.2, still others 6.3. The differences did not reflect disagreement so much as refinement. The European Mediterranean Seismological Center often relies on magnitude scales that emphasize surface wave amplitudes or body wave properties. The United States Geological Survey, by contrast, calculates moment magnitude from the total energy released. As additional seismic records arrived from around the world, analysts updated their estimates, converging on values that explained why the numbers shifted in the news cycle. Earthquakes are not single numbers carved in stone. They are evolving interpretations of complex physical events. The aftershock sequence behaved almost exactly as history would predict. Later on September 25th, a magnitude 5.8 tremor rattled the same region, a large aftershock by seismological standards, smaller than the main shocks, but still capable of toppling weakened walls and fraying nerves. This pattern fits Amori's law, first described in the early 20th century, which shows how aftershock frequency decays with time. The largest usually strike within days, while smaller echoes can continue for weeks, months, sometimes years. For millions across Venezuela and Colombia, the statistics translated into lived experience. The shallow depth of both main ruptures amplified surface shaking, forcing evacuations in high-rise buildings from Maracaibo to Caracas. Social media carried shaky videos of chandeliers swinging like pendulums, windows rattling, and stairwells filling with people hurrying into the streets as emergency protocols snapped into action. Initial reports suggested damage was modest, but assessment teams spent days combing through neighborhoods, inspecting both visible cracks and subtler structural weaknesses that might haunt the region for years. The geology of the Maracaibo Basin explains why the ground can convulse so violently. Formed through long contests between the Caribbean and South American plates, the basin hosts a tangle of fault systems that absorb and redistribute stress. Lake Maracaibo itself occupies a graben, a sunken block of crust bordered by normal faults that remain active to this day. Ironically, the same tectonic processes that carve basins and faults also created the sedimentary traps that make this region rich in petroleum energy buried by the very forces that still threaten it. Seismologists remind us that depth estimates come with uncertainty, particularly in geologically complex terrain. The 7.8-kilometer figure for the first quake and the 14-kilometer depth for the second represent best fits from multiple seismic stations. Both lie squarely in the brittle upper crust, where rock fractures violently rather than deforming plastically as it does deeper within the earth. The timing of these ruptures inevitably raised questions. Could external factors, solar storms, atmospheric pressure changes, or cosmic influences play a role? Here, the scientific consensus is firm. The U.S. Geological Survey and international seismological organizations agree. There is no reliable correlation between space weather and earthquakes. Decades of statistical studies have failed to show predictive relationships between solar flares, geomagnetic storms, or coronal mass ejections and seismic events. Some research has explored subtler effects. Shifts in atmospheric pressure can load faults slightly, and earth tides induced by the moon and sun measurably flex the crust. But these forces are orders of magnitude smaller than the stress needed to trigger quakes unless a fault is already on the brink of failure. Meanwhile, the global centroid moment tensor database provided crucial forensic details. Its so-called beach ball diagrams, derived from seismic waveforms, revealed the orientations of the ruptured faults and the directions of slip. These models allow researchers to reconstruct which fault planes moved and to infer how stress redistributed across the region, information vital for assessing which segments might face elevated risk in the near future. This is the realm of statistical seismology, not prediction, but probability. After a major quake, the likelihood of additional large events in the same region temporarily increases due to aftershock clustering and stress transfer. That probability slowly decays over weeks and months, but no method exists to specify the exact time or place of the next rupture. What can be done is preparation. Building codes and emergency systems remain the only true defense in seismically active zones. Zulia State's experience suggests that modern standards helped blunt the impact. The relative moderation of damage, despite twin quakes of magnitudes 6.2 and 6.3, reflected not only luck in timing. The events struck when many people were at home rather than in vulnerable offices or schools, but also gradual improvements in construction. Could stronger earthquakes strike here again? Absolutely. History records that the fault systems around Lake Maracaibo are capable of magnitude 7 events. The tectonic setting ensures that such ruptures will recur on geological timescales. What no one can say is whether that means days, years, or decades. For now, seismology can only describe the physics. Plates grind past each other at centimeters per year. Stress accumulates invisibly, and when rock strength is exceeded, centuries of strain collapse into seconds of violence. As the aftershocks continued to ripple through the crust, attention shifted skyward, because even as the Earth reminded us of its latent power, the Sun was in the midst of its own convulsions, unleashing storms on scales that make terrestrial earthquakes seem like whispers against the roar of a star. Part 7. The Sun at maximum solar. Solar cycle 25 reached its crest in 2024 and 2025, reshaping our normally steady star into something more volatile, a restless giant hurling billion-ton clouds of plasma across the solar system. On September 24th and 25th, as twin novae illuminated southern skies and earthquakes ruptured Venezuelan ground, the sun itself was near maximum fury. The evidence came not from myth or metaphor, but from radio telescopes. Each day, instruments recorded the 7 centimeter radio flux, a benchmark measure of solar activity. During late September, values hovered around 180 to 190 solar flux units. For context, anything above 150 signals elevated conditions. Beyond 200, the Sun enters territory where major space weather events become likely. The late September readings painted a portrait of a star humming with energy. Sunspots told a similar story. These dark blemishes, often larger than Earth itself, mark regions where magnetic field lines punch through the photosphere, choking off the normal upwelling of heat. In their cores, field strengths can reach 3,000 Gauss, about 6,000 times stronger than Earth's magnetic field at the surface. More sunspots mean more opportunities for magnetic lines to knot, twist, and snap, releasing their pent-up energy as solar flares or coronal mass ejections. At solar maximum, the Sun's field resembles not the orderly dipole of solar minimum, but a tangled skein of magnetic chaos. Active regions, archipelagos of sunspots linked by vast magnetic loops, can persist for weeks, rotating across the solar disk like storm systems on a star. Some flare quietly, others unleash eruptions so spectacular they are tracked by spacecraft throughout the inner solar system. Coronal mass ejections are the most dramatic of these outbursts. They begin when coronal field lines become so stressed that they suddenly reconnect, transforming magnetic energy into the kinetic energy of charged particles. The result is staggering. Clouds of plasma weighing billions of tons launched into space at speeds ranging from 250 kilometers per second to more than 3,000 for the most violent blasts. Such storms can traverse the gulf between Sun and Earth in just 1 to 4 days. To track them, NOAA's Space Weather Prediction Center employs the WSA-Enlil model, a three-dimensional simulation of solar wind and CME propagation. Enlil divides interplanetary space into a computational grid stretching from the corona out past Earth's orbit, calculating how solar wind speed, density, and magnetic orientation evolve as plasma clouds travel outward. The model excels at forecasting arrival times and broad intensity, though it cannot resolve every fine-scale twist of CME structure. Seasonal geometry adds its own complications. Around the equinoxes, Earth's magnetic field tilts into a configuration that favors reconnection with the interplanetary magnetic field. This Russell-McFerrin effect means that storms striking in September or March can produce geomagnetic disturbances stronger than expected, even from modest solar eruptions. The result is a seasonal amplification, a reminder that timing and geometry matter as much as raw solar output. The effects extend well beyond the dancing auroras that capture public imagination. Geomagnetic storms can interfere with high-frequency radio channels vital to aviation and shipping. They can swell Earth's upper atmosphere, increasing drag on satellites and forcing operators to correct orbits. In severe cases, induced currents in long power lines can stress or even disable electrical grids. NOAA maintains scales to communicate these risks. The G scale for geomagnetic storms, the scale for solar radiation storms, and the R scale for radio blackouts. These indices help industries anticipate and mitigate disruptions when the Sun turns tempestuous. The interaction between coronal mass ejections and comets provides a natural laboratory for plasma physics under conditions we cannot recreate on Earth. A comet's ion tail forms when solar wind strips electrons from molecules in the coma, producing charged particles that align with solar magnetic field lines. These tails can stretch millions of kilometers, visible markers of invisible magnetism. When a CME collides with such a tail, the results can be spectacular. In 2007, The European Space Agency's Stereo spacecraft recorded one of the most dramatic examples. ACME completely severed the ion tail of Comet Encke. Over several hours, the detached streamer drifted into space while a new tail formed behind it, a vivid demonstration of magnetic reconnection at work. In 2025, the stage was even grander. With solar cycle 25 at its most active, the Sun provided a turbulent backdrop just as 3I Atlas, the newly discovered interstellar visitor, entered the inner solar system. Unlike Oumuamua or Borisov, which passed through under quieter solar conditions, this traveler from another star system found itself moving through an environment thick with storms. Plasma, magnetism, and alien ice were about to meet in a cosmic experiment, orchestrated not by human design, but by the rhythm of the Sun itself. Unlike its predecessors, which slipped through quieter phases of the solar cycle, this interstellar traveler entered our system during peak turbulence. Solar cycle 25 was roaring at near maximum, its rhythm marked by frequent coronal mass ejections, and the geometry of the visitor's path only heightened the drama. 3I Atlas was not skimming above or below the solar system's plane, but moving directly through the ecliptic, the crowded stage where planets, dust, and magnetic storms most often collide. That trajectory maximized the odds of meaningful interaction, setting the stage for a confrontation between alien ice and solar fire. The physics behind CME propagation is as complex as it is grand. At its heart lies magnetohydrodynamics, a science that spans scales from the spiral of individual charged particles to plasma structures larger than planetary orbits. When a fast CME overtakes slower solar wind ahead of it, the collision creates compression regions and shock fronts. In these zones, particles are whipped to extraordinary energies, producing the same kind of cosmic rays that ripple through detectors on Earth. When multiple CMEs erupt in succession, their interactions become even more chaotic. They may merge into massive compound storms, or their tangled magnetic fields may twist together into exotic configurations that amplify both particle acceleration and magnetic reconnection. Professional forecasters watch this ballet of plasma with an array of instruments. NASA's Solar Dynamics Observatory stares continuously at the solar surface, imaging the corona in multiple extreme ultraviolet wavelengths to capture eruptions as they unfold. The veteran Solar and Heliospheric Observatory maintains vigilance from another vantage, detecting CMEs erupting from the Sun's far side. Between Earth and Sun, the Advanced Composition Explorer samples the solar wind directly, its measurements of speed, density, and embedded magnetic field orientations serving as an early warning system before storms reach Earth. Beyond the professionals, a distributed human network contributes its own data. Amateur radio operators, scattered across the globe, act as real-time monitors of space weather effects. During geomagnetic storms, their high-frequency signals can bounce farther than usual, reaching continents normally beyond line of sight. At other times, the same disturbances create absorption zones where communication collapses entirely. Reports shared across this informal community provide a living map of ionospheric behavior, complementing official monitoring stations with ground-level human experience. Cycle 25 itself has not been a simple crescendo. Many researchers describe its profile as double-peaked, a pattern seen in earlier solar cycles. The first peak came in 2024, but activity remained elevated through 2025, extending the maximum phase longer than expected. This lingering intensity suggests that the heightened risk of solar terrestrial disruption may endure into 2026, prolonging the window for both spectacular auroras and potentially hazardous space weather events. Aurora photography in particular, has surged during this cycle. Social media streams overflow with images of luminous curtains rippling across night skies, green from oxygen at lower altitudes, red from oxygen at higher levels, and purples and blues from nitrogen emissions. These ethereal displays are the visible signature of charged particles, guided by Earth's magnetic field, colliding with atmospheric atoms and releasing photons as they relax back to ground states. To the public, they are works of art. To scientists, they are diagnostics, maps drawn in light of how Earth's magnetosphere couples with the solar wind. That solar wind carries more than charged particles. It transports magnetic fields lifted from the sun's corona and stretched across the heliosphere as the plasma flows outward. These interplanetary magnetic field lines connect planets, comets, and spacecraft in an unseen lattice that extends all the way to the heliopause, the frontier where solar wind pressure finally balances the pressure of the interstellar medium, nearly 100 times farther from the sun than Earth. Within this magnetic web, objects large and small remain linked to the sun's temperamental heart. By late September 2025, as solar storms propagated through the inner heliosphere, attention narrowed on one extraordinary target. For the first time, an interstellar visitor forged in another star's nursery, hardened during an eons-long journey through the dark, was threading through a solar storm system. 3I. Atlas was approaching its first planetary encounter, moving toward Mars, while space weather forecasters, astronomers, and skywatchers worldwide held their collective breath. It was as though the sun itself had arranged a trial by fire, subjecting the traveler to the full fury of its maximum cycle. Part 8. 3I Atlas on approach. In the pre-dawn hours of July 1st, 2025, the sky offered up something astonishing. Against the slow drift of background stars, the Asteroid Terrestrial Impact Last Alert System ATLAS recorded a faint, comet-like smudge. At first, it seemed ordinary, just another transient among thousands catalogued each year. But within hours, orbital calculations revealed the truth. This was no comet bound to the Sunday, it was an interstellar traveler, only the third ever confirmed by humanity. Its name tells its story. The designation 3I Atlas reflects both lineage and discovery. The prefix marks it as the third officially recognized interstellar object after the enigmatic Oumuamua in 2017 and Comet Borisov in 2019, while Atlas honors the Wide Field Survey telescope that first noticed its subtle movement. Unlike its predecessors, 3I Atlas arrived under uniquely favorable conditions bright enough for telescopes to study in depth, following a path near the ecliptic plane where the planets circle, and entering the solar system during solar maximum, when the sun's storms provide a natural laboratory for studying how interstellar material reacts to stellar fury. The visitor's orbital parameters announce its alien heritage. Its path is unmistakably hyperbolic, with an eccentricity well above 1, proof that it carries too much velocity ever to be captured by the sun's gravity. Its inclination of roughly 175 degrees means it cuts backward through the planetary traffic, retrograde against the familiar flow of the solar system. Models place its size somewhere between a few hundred meters and as much as 15 kilometers, though uncertainties remain wide. Even the largest observatories see it only as a faint, star-like point with a hazy coma, a veil of gas and dust stirred loose by solar warmth. Everything about its scale and mass depends on assumptions, reflectivity, surface composition, activity level, and each assumption remains guesswork for a body forged around another star. October 3rd, 2025, promises to be a milestone in interstellar science. On that date, 3I Atlas will sweep past Mars at just 0.19 astronomical units, 28 to 30 million kilometers. From the Red Planet's orbital fleet, it will be a front-row encounter. ESA's ExoMars Trace Gas Orbiter, NASA's Mars Reconnaissance Orbiter, and other spacecraft will seize the chance. Avi Loeb of Harvard captured the mood best, describing the meeting as a blind date between an interstellar visitor and our neighboring world. The high-rise camera aboard Mars Reconnaissance Orbiter, capable of resolving objects 30 centimeters across on Mars, will achieve a pixel scale of about 30 kilometers when turned on the passing visitor. That resolution cannot sketch the contours of the nucleus, but it may reveal whether the core is compact or diffuse, shedding light on the balance between solid body and expanding coma. Spectroscopy during the flyby carries even greater promise. As sunlight heats the nucleus, volatile molecules will escape, producing spectral signatures of cyanogen, Cn, carbon monoxide, CO, and carbon dioxide, CO2. Detecting these gases would offer direct clues to the object's chemistry, a glimpse into the environment of its birth system, preserved across millions of years of interstellar drift. Amateurs on Earth have played their part, too. Observers from the southern hemisphere first noted an unexpected brightening as 3I Atlas moved sunward, though those preliminary light curves await careful calibration. Binoculars and CCDs alike are being turned skyward. Northern hemisphere astronomers, though less favored by its southerly track, catch the object in early morning when it rises above their horizon. Professional networks, the American Association of Variable Star Observers, the Minor Planet Center, continue to coordinate, pooling nightly reports into a global campaign. Together they track brightness shifts, tail evolution, and spectral changes as the visitor adjusts to the sun's glare. And the story extends beyond October 3rd. After brushing past Mars, 3I Atlas will continue toward its closest approach to the Sun on October 29th, at a distance between 1.36 and 1.4 astronomical units. That keeps it safely beyond Earth's orbit, but well within reach of observatories across the globe and in space. Into early 2026, it will remain visible, giving humanity its longest window yet to study an interstellar messenger, a body not of our system, but passing through, briefly and brilliantly, before returning to the dark between stars. December 19th will bring 3I Atlas into its closest approach to Earth, about 1.8 astronomical units, or roughly 270 million kilometers. To put that in perspective, the visitor will come closer than Mars ever does at its farthest point from us. For astronomers, both professional and amateur, this distance represents a gift. Excellent viewing conditions that will stretch through late 2025 and well into early 2026. Even modest backyard telescopes will have the chance to track this alien wanderer as it glides across our skies. Its behavior near perihelion holds special promise. Solar heating at this stage may awaken volatile compounds that have remained locked in ice for millions of years during its long exile between stars. If released, these gases could trigger dramatic flares in brightness, the growth of tails, or other features that may separate an interstellar visitor from the comets born in our own system. For planetary scientists, this is the great unknown. Will 3I Atlas follow the familiar script of cometary physics, or will it reveal patterns unique to its origins around another sun? One of the most intriguing questions lies in tail morphology. Professional images have revealed ion tails sweeping anti-sunward, as expected, while amateur reports have sometimes described forward-curving dust structures that seem to defy normal cometary behavior. These contradictions are less likely signs of exotic physics and more reflections of the complex mechanics governing different types of tails. Dust tails emerge from radiation pressure, the steady push of sunlight striking microscopic particles expelled from the nucleus. These particles trace graceful arcs, curving under the competing influences of solar radiation and gravity. Depending on the viewing angle, the geometry can make dust tails appear to bend in surprising directions, even forward from certain perspectives. Ion tails, however, follow a very different rulebook. Here, the solar wind strips electrons from gas molecules in the coma, producing charged ions that are swept up along the invisible lines of the interplanetary magnetic field. The result is a straight, narrow tail, always pointing directly away from the sun, but shifting in orientation whenever the magnetic field changes. Together, these two processes weave the iconic double-tailed appearance of active comets, and in 3I Atlas, they may carry the added imprint of interstellar chemistry. Yet even with the world's best instruments, many of 3I Atlas's physical parameters remain shrouded in uncertainty. Direct imaging of surface features is impossible at these distances. Instead, astronomers are forced to rely on indirect measurements. Size estimates, for example, depend on brightness, which in turn requires assumptions about surface reflectivity, composition, and activity, all unknowns for an object formed in another stellar nursery. Some headlines have speculated that 3I Atlas might span up to 15 miles across, but such claims remain highly provisional. More reliable estimates will come only through thermophysical modeling, combining optical brightness with infrared measurements of thermal emission to separate nucleus size from outgassing activity. Activity level itself further complicates the picture. A small but unusually active nucleus can appear deceptively bright, while a large but inert one might remain faint. Gas and dust production skew the apparent luminosity, masking the true scale of the solid core within. Infrared spectroscopy, radio observations, and continued long-term monitoring will be crucial in disentangling these effects. All of this unfolds against a sky staging multiple celestial dramas. As 3I Atlas sweeps inward, its December approach overlaps with another spectacular event that promises to make late 2025 one of the most memorable seasons for skywatchers worldwide. Before we arrive at that moment, though, we must pause to consider the raw physics at play when our sun hurls its storms into the void, and what happens when those storms collide with matter that has spent eons wandering between the stars. Part 8. 3I Atlas on approach. In the pre-dawn hours of July 1st, 2025, the sky offered up something astonishing. Against the slow drift of background stars, the Asteroid Terrestrial Impact Last Alert System Atlas recorded a faint, comet-like smudge. At first, it seemed ordinary, just another transient among thousands catalogued each year. But within hours, orbital calculations revealed the truth. This was no comet bound to the Sunday, it was an interstellar traveler, only the third ever confirmed by humanity. Its name tells its story. The designation 3I Atlas reflects both lineage and discovery. The prefix marks it as the third officially recognized interstellar object after the enigmatic Oumuamua in 2017 and Comet Borisov in 2019, while Atlas honors the Wide Field Survey telescope that first noticed its subtle movement. Unlike its predecessors, 3I Atlas arrived under uniquely favorable conditions bright enough for telescopes to study in depth, following a path near the ecliptic plane where the planets circle, and entering the solar system during solar maximum, when the sun's storms provide a natural laboratory for studying how interstellar material reacts to stellar fury. The visitor's orbital parameters announce its alien heritage. Its path is unmistakably hyperbolic, with an eccentricity well above 1, proof that it carries too much velocity ever to be captured by the Sun's gravity. Its inclination of roughly 175 degrees means it cuts backward through the planetary traffic, retrograde against the familiar flow of the solar system. Models place its size somewhere between a few hundred meters and as much as 15 kilometers, though uncertainties remain wide. Even the largest observatories see it only as a faint, star-like point with a hazy coma, a veil of gas and dust stirred loose by solar warmth. Everything about its scale and mass depends on assumptions, reflectivity, surface composition, activity level, and each assumption remains guesswork for a body forged around another star. October 3rd, 2025, promises to be a milestone in interstellar science. On that date, 3I Atlas will sweep past Mars at just 0.19 astronomical units, 28 to 30 million kilometers. From the red planet's orbital fleet, it will be a front-row encounter. ESA's ExoMars Trace Gas Orbiter, NASA's Mars Reconnaissance Orbiter, and other spacecraft will seize the chance. Avi Loeb of Harvard captured the mood best, describing the meeting as a blind date between an interstellar visitor and our neighboring world. The high-rise camera aboard Mars Reconnaissance Orbiter, capable of resolving objects 30 centimeters across on Mars, will achieve a pixel scale of about 30 kilometers when turned on the passing visitor. That resolution cannot sketch the contours of the nucleus, but it may reveal whether the core is compact or diffuse, shedding light on the balance between solid body and expanding coma. Spectroscopy during the flyby carries even greater promise. As sunlight heats the nucleus, volatile molecules will escape, producing spectral signatures of cyanogen, Cn, carbon monoxide, CO, and carbon dioxide, CO2. Detecting these gases would offer direct clues to the object's chemistry, a glimpse into the environment of its birth system, preserved across millions of years of interstellar drift. Amateurs on Earth have played their part, too. Observers from the southern hemisphere first noted an unexpected brightening as 3I Atlas moved sunward, though those preliminary light curves await careful calibration. Binoculars and CCDs alike are being turned skyward. Northern hemisphere astronomers, though less favored by its southerly track, catch the object in early morning when it rises above their horizon. Professional networks, the American Association of Variable Star Observers, the Minor Planet Center, continue to coordinate, pooling nightly reports into a global campaign. Together they track brightness shifts, tail evolution, and spectral changes as the visitor adjusts to the sun's glare. And the story extends beyond October 3rd. After brushing past Mars, 3I Atlas will continue toward its closest approach to the Sun on October 29th, at a distance between 1.36 and 1.4 astronomical units. That keeps it safely beyond Earth's orbit, but well within reach of observatories across the globe and in space. Into early 2026, it will remain visible, giving humanity its longest window yet to study an interstellar messenger, a body not of our system, but passing through, briefly and brilliantly, before returning to the dark between stars. December 19th will bring 3I Atlas into its closest approach to Earth, about 1.8 astronomical units, or roughly 270 million kilometers. To put that in perspective, the visitor will come closer than Mars ever does at its farthest point from us. For astronomers, both professional and amateur, this distance represents a gift. Excellent viewing conditions that will stretch through late 2025 and well into early 2026. Even modest backyard telescopes will have the chance to track this alien wanderer as it glides across our skies. Its behavior near perihelion holds special promise. Solar heating at this stage may awaken volatile compounds that have remained locked in ice for millions of years during its long exile between stars. If released, these gases could trigger dramatic flares in brightness, the growth of tails, or other features that may separate an interstellar visitor from the comets born in our own system. For planetary scientists, this is the great unknown. Will 3I Atlas follow the familiar script of cometary physics, or will it reveal patterns unique to its origins around another sun? One of the most intriguing questions lies in tail morphology. Professional images have revealed ion tails sweeping anti-sunward, as expected, while amateur reports have sometimes described forward-curving dust structures that seem to defy normal cometary behavior. These contradictions are less likely signs of exotic physics and more reflections of the complex mechanics governing different types of tails. Dust tails emerge from radiation pressure, the steady push of sunlight striking microscopic particles expelled from the nucleus. These particles trace graceful arcs, curving under the competing influences of solar radiation and gravity. Depending on the viewing angle, the geometry can make dust tails appear to bend in surprising directions, even forward from certain perspectives. Ion tails, however, follow a very different rulebook. Here, the solar wind strips electrons from gas molecules in the coma, producing charged ions that are swept up along the invisible lines of the interplanetary magnetic field. The result is a straight, narrow tail, always pointing directly away from the sun, but shifting in orientation whenever the magnetic field changes. Together, these two processes weave the iconic double-tailed appearance of active comets, and in 3I Atlas, they may carry the added imprint of interstellar chemistry. Yet even with the world's best instruments, many of 3I Atlas's physical parameters remain shrouded in uncertainty. Direct imaging of surface features is impossible at these distances. Instead, astronomers are forced to rely on indirect measurements. Size estimates, for example, depend on brightness, which in turn requires assumptions about surface reflectivity, composition, and activity, all unknowns for an object formed in another stellar nursery. Some headlines have speculated that 3I Atlas might span up to 15 miles across, but such claims remain highly provisional. More reliable estimates will come only through thermophysical modeling, combining optical brightness with infrared measurements of thermal emission to separate nucleus size from outgassing activity. Activity level itself further complicates the picture. A small but unusually active nucleus can appear deceptively bright, while a large but inert one might remain faint. Gas and dust production skew the apparent luminosity, masking the true scale of the solid core within. Infrared spectroscopy, radio observations, and continued long-term monitoring will be crucial in disentangling these effects. All of this unfolds against a sky staging multiple celestial dramas. As 3I Atlas sweeps inward, its December approach overlaps with another spectacular event that promises to make late 2025 one of the most memorable seasons for skywatchers worldwide. Before we arrive at that moment, though, we must pause to consider the raw physics at play when our sun hurls its storms into the void, and what happens when those storms collide with matter that has spent eons wandering between the stars. Part 9 Ampere Coming Comet Show. While 3I Atlas has dominated headlines as the first interstellar visitor of the decade, October 2025 promises a second sky spectacle that could rival or even eclipse it. Comet C divided by 2025 R2, discovered not by a professional observatory but by the eyes of an amateur astronomer, is on course for a dramatic close approach to Earth on October 20th and 21st, with projections suggesting it could reach naked-eye brightness just as 3I Atlas brushes past Mars. Its discovery story highlights the power of citizen science in the modern age. The Solar and Heliospheric Observatory, or SOHO, maintains constant watch on the Sun, its SWAN instrument mapping hydrogen emissions throughout the heliosphere. From time to time, this mapping catches comets in the act of outgassing as they heat up on their inward journeys. In September 2025, Russian amateur astronomer Vladimir Bezugli was combing through the publicly available SWAN images when he noticed an anomaly, a brightening object not listed in any database. His careful cross-checks against known asteroids and comets confirmed the candidate, and orbital calculations soon established it as a long-period comet, making its first recorded approach to the inner solar system. The timeline could not have been more dramatic. Just days after its discovery, Comet SWAN passed perihelion on September 12, 2025. The rapid brightening that first caught Bezugli's attention was the direct result of solar heating at closest approach, which liberated frozen gases, swelling the coma and sculpting the first visible tails. From that moment, the comet entered the collective watch list of professionals and amateurs alike. Orbital geometry favors October observations across both hemispheres. Southern observers initially had the advantage, but as the weeks progressed, the comet climbed higher for northern observers, making it accessible to the widest swath of humanity. Predictions suggest a peak brightness of magnitude 4 to 6 dimmer than the brightest stars, but visible to the naked eye under dark skies. With binoculars or small telescopes, its coma and tails would blossom into detail. Yet cometary forecasts are notoriously unreliable. Fresh comets, making their first recorded approaches, often surprise observers, sometimes exceeding predictions spectacularly, other times fizzling into faint smudges. Conditions in late October align perfectly for spectacle. The new moon falls on October 20th and 21st, ensuring skies free of lunar glare. At the same time, the annual Orionid meteor shower fragments of Comet Halley, streaking into Earth's atmosphere, reaches peak activity. For sky watchers, this could create a once-in-a-generation tableau: a bright comet, dozens of meteors per hour, and the ongoing evolution of 3-1 Atlas, all visible during the same long nights. The contrast between the two comets deepens the scientific stakes. Comet SWAN is a long-period solar system native, born in the icy depths of the Oort cloud some 4.5 billion years ago. Its sudden appearance is likely the result of gravitational nudges from passing stars or galactic tides, sending it sunward for the first time. By comparison, 3I Atlas comes from another star entirely, carrying the chemistry of an alien nursery. Both likely harbor similar volatiles: water, ice, carbon monoxide, carbon dioxide, organic molecules, but their histories could not be more different. One speaks of the early days of our solar system. The other whispers of conditions in a stellar system we may never know. For photographers, October becomes a playground. Wide-field cameras may capture both objects in the same frame, glowing against the autumn constellations. Time-lapse sequences could reveal changes in coma shape, tail structure, and brightness as solar wind conditions shift. Side-by-side comparisons promise not just beauty but science, highlighting how a comet born here behaves next to a visitor from afar. The unpredictable nature of comets adds an edge of suspense. Some remain stubbornly faint, but others erupt into brilliance, their tails stretching across the sky, bright enough to outshine city lights. October 2025 holds the possibility of such a transformation, turning Comet SWAN from a scientific curiosity into a cultural phenomenon, a comet for all to see, arriving in the same season as an interstellar messenger. Not every comet fulfills the hopes of sky watchers. Some fail to brighten, fading back into obscurity, While others fragment under the stress of solar heating, their disintegrating nuclei, scattering the very material that once promised spectacle. Comet Swan's brief observational record makes predictions especially difficult. Unlike periodic comets that return again and again, offering astronomers the chance to build models of behavior across multiple apparitions, new long-period comets have no precedent. Their outgassing rates, brightness curves, and structural resilience under solar heat remain mysteries until revealed in real time. Yet therein lies the thrill. The potential for dramatic tail development adds enormous visual allure to October's viewing prospects. Both dust and ion tails may flare into prominence under the elevated solar wind conditions of solar maximum. And if fortune allows, disconnection events when a coronal mass ejection severs a comet's ion tail could be captured by telescopes, granting rare live demonstrations of plasma physics on a cosmic stage. Amateur comet observers play a central role in this unfolding drama. Visual magnitude estimates, made by comparing comet brightness with nearby stars of known magnitude, provide vital data that professionals cannot collect continuously. Digital cameras and CCD systems extend this coverage, measuring brightness with precision while preserving records of coma structures and tail evolution. These global networks supply a temporal density of observations that no single observatory could achieve alone. The question of whether Earth might encounter dust from Comet Swan adds speculative intrigue. If our orbit were to cross remnants of past passages, tiny particles could burn through our atmosphere as meteors, creating a new shower. But with Swan a newcomer, its debris trail remains uncharted, making such events highly uncertain. Spectroscopy, meanwhile, offers the chance to unlock each comet's chemical fingerprint. Instruments can detect emission lines from molecules such as CN, C2, OH, and NH2, revealing which compounds sublimate as solar heat strikes the nuclei. Comparing 3I, Atlas, and Comet Swan across these signatures could highlight differences in their birthplaces. One in the cold nursery of our own solar system's Oort cloud, the other forged around a foreign star. Observation logistics matter, too. Urban skies wash away faint details, leaving rural and wilderness sites the best theaters for comet watching. Weather in late October varies sharply by region, demanding flexibility and persistence. Binoculars often outperform telescopes for casual viewing, their wide fields of view revealing the entire spectacle, nucleus, coma, and tail, rather than magnifying fragments. Models such as 7x50 or 10x50 strike the ideal balance between brightness and comfort. The double comet season of October 2025 promises unprecedented opportunities for direct comparison. Observers may note differences in coma color, tail geometry, or overall morphology that reflect each object's unique history. Time-lapse photography across consecutive nights could document how the comets respond to shifting solar wind conditions and evolving viewing angles. Professional campaigns ensure the coverage is equally thorough. The Hubble Space Telescope may capture high-resolution images, resolving structural details impossible to glimpse from the ground. Radio observatories will listen for molecular emissions that betray chemical composition and thermal conditions in the expanding comae. Together, these instruments will assemble a multi-wavelength portrait of two very different messengers sharing the same sky. For the public, the safety considerations are refreshingly simple. Unlike eclipses, comets require no protective filters. The main challenges are practical: finding dark sites, coping with weather, and keeping equipment stable during long, cold nights. Astronomy clubs, schools, and observatories are already planning public events, turning October into a global classroom where science meets wonder. As the month draws near, the convergence of phenomena becomes staggering. An interstellar visitor threads past Mars. A long-period comet surges toward peak brightness. Solar storms pulse outward from a restless star, and in Venezuela, aftershocks still ripple through fractured crust. Together, they form a timeline that stretches from the deep Earth to the edge of interstellar space, a cascade of events that unsettles our sense of coincidence. But before we confront the deeper questions this clustering raises, we must turn to something older and more intimate, the human mind itself, and its instinctive drive to find patterns in the storm. Part 10. Cosmic Coincidences or Patterns. In the closing days of September 2025, the universe seemed to compress its dramas into a single week. It began on the night of September 23rd, when a point of light bloomed unexpectedly in the constellation Centaurus. V1935 Centauri, a white dwarf stealing gas from its companion star, had reached its breaking point. Thermonuclear fire flared across its surface, and the explosion that had truly happened millennia ago finally revealed itself to human eyes as a sudden star where none had been before. Barely a day later, the violence shifted from sky to soil. At 22:21 UTC on September 24th, Venezuela's Zulia state shuddered under a magnitude 6.2 earthquake. Buildings swayed, chandeliers swung, and alarms echoed across Maracaibo and Caracas. The rupture tore open just 8 kilometers beneath the ground, shallow enough to unleash intense shaking across borders and into the Caribbean. But the Earth had more to give. In the early hours of September 25th, only 5.5 hours later, a second rupture struck the same fault system. This time it measured 6.3, releasing nearly double the energy of the first. And as dawn rose, a 5.8 aftershock added its own punctuation, confirming that the fault lines beneath Lake Maracaibo had entered a volatile cycle. That same day, above the southern horizon, another stellar eruption announced itself. V7994 Sagittarii brightened suddenly in the constellation of Sagittarius, becoming the second naked-eye nova in less than 48 hours. 2 stellar explosions, 2 major earthquakes, all unfolding almost in lockstep, a choreography that felt more like myth than geophysics. Meanwhile, models of the sun's behavior traced a different kind of upheaval. The Enlil simulations run by space weather forecasters showed coronal mass ejections, billion-ton clouds of plasma, threading through the inner solar system at the very moment an interstellar object, 3I Atlas, was crossing the ecliptic. The geometry was uncanny, a wanderer from another star brushing through a storm launched by our own. October would only heighten the sense of cosmic convergence. On the 3rd, 3I Atlas would swing past Mars, close enough for orbiters circling the red planet to turn their cameras outward and attempt the first detailed study of an interstellar nucleus. Weeks later, on the 20th and 21st, Earth would find itself under a new moon sky as Comet Swan reached closest approach. Its timing was exquisite. A brightening comet, the Orionid meteor shower peaking, and 3I Atlas still arcing sunward. By the 29th, the interstellar visitor would reach perihelion, just 1.36 astronomical units from the Sun, its volatile ices hissing into space beneath the furnace of solar maximum. Taken separately, each event has a rational explanation. Earthquakes follow stress accumulation and transfer along fault systems. Novae erupt when white dwarfs accumulate enough hydrogen from their companions to ignite runaway fusion. Solar storms obey the tangled physics of magnetic reconnection in the corona. Interstellar objects wander into our system by chance, their orbits carved by gravitational slingshots across galactic time. Yet seen together, 2 stars exploding, two earthquakes rattling the same region within hours, solar storms threading across an interstellar path, a comet brightening just as another visitor brushes past Mars. The clustering feels uncanny. Science insists on boundaries. The United States Geological Survey maintains that no mechanism links solar activity to seismic events. Astronomers point out that nova eruptions follow stellar physics, not earthly rumblings. Solar physicists study CME, comet interactions, as plasma dynamics, not as omens. And yet the human mind, evolved to detect patterns, cannot help but read significance in such compression. It is apophenia, perhaps the same instinct that helped our ancestors predict seasons, weather, or danger in the rustle of the grass. But it is also poetry, when coincidence arranges itself so tightly that skepticism and wonder collide. What late September and October 2025 offered was not proof of hidden connections, but a rare tableau: stars, planets, comets, and the Earth itself all flaring, shaking, or erupting in near synchrony. The story is told not just in seismographs and telescopes, but in the way human perception stitches disparate data into narrative. And sometimes, even when science explains the mechanics, the clustering still feels like the universe telling a story in its own voice. Across history, human beings have carried an instinct to look at clustered events and ask whether they mean something more. Even in our scientific age, that impulse remains. We live in a world where seismographs and satellites can map each rupture and explosion with precision. Yet the emotional weight of several dramatic events unfolding at once still presses on us. Scientific knowledge coexists with deeper psychological needs. The need to sense order in apparent chaos, to see design where physics insists on coincidence. The challenge, then, is balance. Rigorous science must remain our guide, but acknowledging the aesthetic and emotional impact of these convergences does not weaken that rigor. We can marvel at the timing of cosmic flares and terrestrial tremors without surrendering to mysticism. We can allow wonder to breathe alongside skepticism. Both responses, when kept distinct, enrich our understanding. Two interpretations stand before us. The first is grounded, the clustered but unrelated view. Stellar physics explains why white dwarfs explode into novae. Plate tectonics explains why Venezuelan rock breaks along fault lines. Solar physics explains coronal mass ejections, magnetic fields snapping and releasing plasma into space. Orbital mechanics explains the approach of comets and interstellar wanderers. Each system runs on its own timetable, governed by established laws that operate independently of one another. The second interpretation reaches further, into speculation. It suggests that these phenomena might not be so separate after all, that there may be subtle, undiscovered links weaving the fabric together. This perspective does not reject physics, but humbly concedes that our physics may still be incomplete. Perhaps hidden correlations exist, waiting for discovery, connections that stitch together domains we now treat as unrelated. This is the cosmic resonance hypothesis. It remains speculative, but speculation itself can be valuable, provided it stays clearly marked as such and generates predictions that can be tested. Meanwhile, other explanations require no speculation at all. The autumn equinox brings the Russell-McFerran effect, a seasonal geometry that naturally enhances geomagnetic activity. Solar storms flare more readily at this time of year, not because of mysterious cosmic design, but because of the way Earth's magnetic axis tilts relative to the Sunday. In seismology, seasonal patterns have been noted in some regions too, though the mechanisms remain subtle and uncertain. Culture adds another layer still. Comets have long embodied change and upheaval. Earthquakes symbolize the ground, reminding us it is alive. Stellar explosions carry the archetypal weight of renewal through destruction. These associations are as old as human storytelling, patterns imprinted on our psychology, whether or not they reflect physical causation. They enrich the narrative without needing to dictate the science. So the invitation is simple. Hold both frames lightly. Respect the strength of established knowledge, but leave room for wonder. We can recognize the synchronistic feel of cosmic events clustering without assuming that hidden hands guide them. We can test speculative connections without pretending they are fact. We can embrace beauty and probability together. Perhaps the most honest stance is also the most humble. To admit uncertainty, to stay open to discovery, to let both science and imagination have their place. The September-October convergence offers material for both rigorous analysis on one hand, archetypal resonance on the other. What matters is clarity about what we observe, what we hypothesize, and what we truly know. And it is here, at the border between speculation and science, that one long-debated idea rises again: the possibility that space weather, those great storms of plasma and magnetism launched by our star, might in some way influence the trembling of Earth's crust. A mechanism remains elusive, the evidence uncertain, but the question lingers, daring us to look closer. Part 11. Space Weather and Earthquakes. The suggestion that solar storms might, in some hidden way, influence the timing of earthquakes has lingered at the edges of geophysics for decades. It remains one of the most persistent and controversial ideas in Earth-space science. Again and again, researchers have reported correlations between bursts of solar activity and seismic events on our planet, and yet through all those decades of study, no widely accepted mechanism has explained how electromagnetic tempests, erupting 93 million miles away, could trigger sudden ruptures in Earth's crust. One of the more intriguing proposals in recent years comes from researcher Stephen Burns. He argued that when a dense, high-speed stream of solar wind suddenly gives way to the thin, sluggish background flow, the drop in density could create a kind of electromagnetic vacuum. In theory, this shift might subtly tug at Earth's magnetosphere, altering its pressure balance. From there, the disturbance could cascade downward, changes in the magnetosphere reshaping ionospheric currents, those currents inducing faint electromagnetic fields, and those fields propagating into Earth's crust, where they might affect piezoelectric stresses in crystalline rocks. It is a chain of possibilities, each link plausible in itself, yet at every step the signal grows weaker, the effect more attenuated. The actual measurements involved are vanishingly small, magnetic variations of a few teslas, stress changes at the level of microstrains. These quantities are thousands of times below the threshold needed to push a locked fault into sudden failure, unless that fault was already teetering on the edge. The physics is real, the couplings exist, but their magnitudes seem insufficient to move tectonic plates. What is firmly established, instead, is the literature of correlations. For decades, papers have appeared claiming statistical connections, spikes in solar flare activity, lining up with seismic clusters, geomagnetic storms followed by earthquake swarms, indices of solar wind linked with regional earthquake catalogues. At first glance, some of these correlations appear compelling, statistically significant, but many fade under replication. Apply the same methods to different decades, to other fault systems, to broader global data sets, and the signal often vanishes. Publication bias deepens the problem. Positive findings attract attention. Null results quietly disappear. As a result, the scientific literature can give an illusion of consensus where none exists, a landscape in which striking correlations are published, cited, and recited, while studies that find nothing remain buried. Meta-analyses that combine multiple datasets often reveal the pattern. Effect sizes shrink as sample sizes expand, as statistical rigor improves, as biases are corrected. This is why the United States Geological Survey, supported by international seismological organizations, has taken a firm stance. No reliable correlation exists between solar activity and earthquakes. The conclusion rests on exhaustive statistical comparisons, global earthquake catalogs tested against multiple solar cycles worth of space weather data. Once proper controls are applied for temporal clustering and selective reporting, the apparent correlations dissolve. Still, curiosity persists, and some researchers continue to probe subtler possibilities. Could geomagnetic storms influence atmospheric pressure in ways that load stress onto faults? In principle, yes, but the variations involved are tiny, less than 1 millibar, smaller than normal weather fluctuations, which themselves show no convincing links to seismicity. Could geomagnetic induction play a role? Strong solar storms can indeed drive electric currents through Earth's crust, especially in regions rich with underground water or conductive minerals. Such currents might influence pore pressures or local chemistry in fault zones, but again, the magnitudes are far below what seismology tells us is required to trigger rupture. The most persuasive evidence for celestial influences on earthquakes does not come from solar storms at all, but from gravity. Earth tides, the slow flexing of the crust under the combined pull of sun and moon, have been shown to modulate seismicity. Faults, already on the brink, sometimes slip more readily during periods of maximum tidal stress. These gravitational effects are measurable, well understood, and physically direct. Planetary alignments, by contrast, inspire popular imagination but exert forces that are negligible, dwarfed by the tides raised each day by our own moon. And so the hypothesis endures, hovering between possibility and improbability. The coupling pathways exist, but the scale seems insufficient. The correlations appear, but often evaporate under scrutiny. Between the promise of cosmic connection and the discipline of seismology lies a scientific riddle that continues to invite attention. Even if the mainstream verdict remains clear, earthquakes belong to the restless Earth, not to storms raging across the surface of the Sunday. Testing whether solar storms might nudge the timing of earthquakes is not as simple as matching dates on a calendar. The challenge lies in untangling genuine physical relationships from the tangle of statistical artifacts that nature produces on its own. Earthquakes follow intricate patterns. Aftershocks ripple outward from major ruptures, faults cluster spatially along tectonic boundaries, and seismicity ebbs and flows in temporal waves. Space weather, too, has its own cycles and rhythms, auto-correlated indices, repeating periodicities, bursts of activity that can align by sheer coincidence with seismic records. Place these two complex datasets side by side, and patterns are bound to emerge. The danger is mistaking coincidence for causation. To move beyond suggestion requires discipline. Proper tests must be defined before the data are examined. Hypotheses should specify time windows, regions, and statistical thresholds in advance, not retrofitted to match a tempting result. Blind protocols, where earthquake catalogs are analyzed without knowledge of concurrent space weather, could strip away unconscious bias and expose only the strongest signals. Such rigorous methods are rare in the literature, yet they are precisely what would be needed to establish a genuine connection. What, then, would count as compelling evidence? First, a physical mechanism must be demonstrated, either through laboratory experiments or theoretical models, showing that electromagnetic or particle effects could exert stress on crustal rock at levels meaningful to fault mechanics. Second, statistical relationships would need to demonstrate predictive skill correlations that persist when tested prospectively against new data rather than evaporating under replication. Third, any authentic connection would almost certainly be conditional, operating in specific tectonic environments or under certain fault geometries. A universal influence, affecting every seismic region equally, seems implausible given the vast differences in geology and stress regimes across the planet. The Venezuelan earthquake sequence of September 2025 occurred during heightened solar activity, adding fuel to the debate. But coincidence is not causation. The region itself is tectonically restless, a collision zone where magnitude 6 earthquakes occur with irregular but predictable rhythm as stress accumulates along the Caribbean, our South American plate boundary. If space weather exerts any influence at all, it would most likely act as a faint nudge, advancing a rupture already poised to fail by hours or days, not conjuring earthquakes that would not otherwise occur. Seismology paints earthquakes as products of local physics, the evolution of stress along a fault, the strength of the rocks, the stochastic processes inherent in complex, non-linear systems. External factors, solar storms, atmospheric pressure shifts, even geomagnetic fluctuations may leave fingerprints too faint to detect beside the dominant grinding of tectonic plates. The most scientifically honest position is therefore both cautious and humble. Theoretically, subtle couplings cannot be ruled out. But empirically, no convincing evidence shows they matter at scales detectable to our instruments or useful to hazard forecasting. Future work must precede physics. First, mechanisms must be demonstrated in principle before statistical fishing expeditions in observational data. For earthquake preparedness, this distinction matters. Space weather forecasts offer no practical guidance. Building codes, emergency planning, and probabilistic hazard assessments remain the foundation for public safety, not solar indices. Yet as we close one line of speculation, another opens. If the sun's storms struggle to reach Earth's crust, could energy from distant stars reach us instead? Could the fury of stellar explosions shape our climate or geology over longer timescales? The scales of energy and distance involved shift dramatically here. A nova, such as V1935 Centauri or V7994 Sagittari, releases energy equivalent to the Sun's output over 10,000 years, about 10 to the 43rd joules. Impossibly vast in human terms, enough to fuel civilization for billions of years. And yet, these blasts occur thousands of light-years away. Their energy, spreading in all directions, obeys the inverse square law. By the time the photons arrive, they have thinned into a whisper, no more powerful than bright starlight. The reality is stark. The nova light that dazzled us in September 2025 began its journey millennia ago, when agriculture was still an experiment for early human societies. What finally reached Earth was beautiful but harmless, a trickle of photons, perhaps a few extra per square meter, less additional energy than the beam of a flashlight held at arm's length. Enough to paint the night sky, not enough to stir our atmosphere or warm a single cup of water. Supernovae tell a different story. These are the cosmic giants, explosions capable of outshining entire galaxies. A detonation within 50 light-years could flood Earth with gamma rays and X-rays powerful enough to erode the ozone layer, exposing the surface to deadly ultraviolet light. Some mass extinctions in Earth's deep past have been tentatively linked to such nearby blasts, though the evidence remains debated and elusive. The mechanisms here are not about warming but chemistry. Radiation from a nearby supernova could shred atmospheric molecules, altering climate through ozone depletion and cascading feedbacks. But novae like those we observed in September brilliant, yes, but distant and modest compared to their supernova cousins pose no such threat. They are messengers of stellar evolution, not harbingers of terrestrial catastrophe. High-energy photons, unleashed by stellar explosions, have the power to split nitrogen and oxygen molecules in Earth's upper atmosphere, initiating chains of reactions that form nitrogen oxides compounds that can shred ozone through catalytic cycles. A weakened ozone layer would mean more ultraviolet sunlight reaching Earth's surface, exposing ecosystems to heightened radiation and disrupting climate through complex feedbacks. This is the kind of planetary consequence a nearby supernova might trigger. But novae like those that flared in September 2025 sit too far away, their energies dispersed across interstellar gulfs until they arrive as little more than starlight. Another proposed mechanism, cosmic rays accelerated by stellar shock waves, offers a more subtle route by which stars might influence Earth's climate. In theory, these high-energy particles could seed cloud formation by acting as condensation nuclei in the atmosphere. More cosmic rays, more clouds, more reflection of sunlight back to space, a potential climate lever. Yet the evidence remains fragmentary and contested. Laboratory studies and atmospheric data yield tantalizing hints but no consensus. The novae of September will not alter this debate. Their accelerated particles, if any, would need thousands of years to reach our solar system, long after the flashes we saw have faded. By then, they will be indistinguishable from the steady drizzle of galactic cosmic rays that already bathe Earth. Popular narratives often blur these distinctions, conflating novae with supernovae, exaggerating their terrestrial influence, and fueling headlines about star explosions shaking our climate. The reality is less sensational, but no less awe-inspiring. The total energy from both September novae that will ever touch Earth is less than the sunlight our planet receives in a single second. No atmospheric chemistry will change. No climate signals will register. What we witnessed was spectacle, not threat. That does not diminish the legitimate science of stellar influences over geological time. Earth does carry isotopic scars of nearby supernovae. The radioactive isotope iron 60, forged in stellar furnaces and ejected by cataclysmic blasts, has been found in deep-sea crusts and polar ice. These traces suggest that, 2 to 3 million years ago, shock waves from dying stars brushed our planet, sprinkling us with material from beyond the solar system. Some researchers have speculated about links between such supernova encounters and Earth's climate history, perhaps even influencing the pacing of ice ages. The evidence remains debated, the mechanisms uncertain, the conclusions far from settled. Contrast these million-year timescales with the immediacy of September 2025. The novae we admired V1935 Centauri and V7994 Sagittarii delivered only beauty, not change. They remind us of the difference between astronomical grandeur and terrestrial impact. Our climate remains driven by forces far closer and more familiar: the steady output of the sun, the chemistry of our atmosphere, the restless churning of oceans, the violence of volcanoes. And yet, the impulse to link distant cataclysms to earthly tremors is deeply human. Our ancestors looked skyward and wove omens into comets and eclipses. Today, we lace the same narratives through news cycles and online commentary. The clustering of novae, earthquakes, solar storms, and an interstellar visitor in late 2025 provides irresistible material for this pattern-seeking instinct. But physics insists on perspective. Stars explode across the galaxy every year. Faults rupture beneath Venezuela because tectonic plates grind and slip. The sun casts off plasma clouds as part of its natural cycle. These domains intersect only in our minds, where coincidence feels like destiny. Still, One cosmic actor remains whose story belongs not to speculation, but to direct observation. Unlike the distant novae, it is here, threading through the inner solar system in real time. It is alien in origin, yet present in our skies. The interstellar visitor, 3I Atlas, offers a rare and immediate opportunity to study how matter forged around another star responds to the storms and light of our own. Part 12: Interstellar Visitors as Solar. 3I Atlas is not just another visitor from the void. It may prove to be the most sensitive natural probe humanity has ever encountered for studying the dialogue between our sun and material forged in alien stars. Oumuamua came and went too quickly, a fleeting mystery. Borisov lingered longer, but remained far from the inner stage. This third interstellar traveler, however, threads itself directly into the theater of solar weather, offering a rare chance to watch our star shape and sculpt matter that has spent millions of years wandering the darkness between stellar systems. Its geometry alone elevates 3I Atlas to a scientific prize. Unlike its predecessors, which slashed through the solar system on steeply inclined paths, this object runs close to the ecliptic plane, the very disk where the planets orbit, and where solar wind density and magnetic complexity reach their fiercest. And it does so during the roaring maximum of solar cycle 25, when coronal mass ejections erupt with frequency and the sun's magnetic field ties itself into knots of chaotic power. Astronomers often describe comets as natural instruments, free-floating magnetometers, and plasma sensors. Their ion tails stretch like luminous streamers, tracing invisible lines of magnetism carried outward by the solar wind. Subtle shifts in orientation, sudden bends, brightening, or even disconnection events record the passage of shocks and disturbances that ripple through the heliosphere. For decades, researchers have mined these changes for data, using comets as remote laboratories in space. But 3I Atlas carries a difference written into its very ice. It is not of this system. It condensed in another stellar nursery, under alien chemistries, perhaps billions of years ago. If our sun's storms alter its behavior, we are witnessing the first tangible exchange between the magnetic breath of our star and the frozen memory of another. The Mars flyby on October 3, 2025, turns this opportunity into a celestial experiment. At a distance of 0.19 astronomical units, around 28 million kilometers, ESA's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter will have front-row seats. From their vantage points, they will capture perspectives Earth cannot provide. The high-rise camera, designed to image Martian boulders at 30-centimeter resolution, will shrink its gaze across space to pixel scales of about 30 kilometers on the interstellar target. It will not reveal the nucleus in fine detail, but it can test whether the brightness we see comes from a compact body or a diffuse coma spreading outward. Even more powerful are the spectrometers riding aboard these orbiters. Built to analyze Martian gases, they can just as readily capture the faint fingerprints of molecules escaping from 3I Atlas as solar heat drives sublimation. Cyanogen, carbon monoxide, carbon dioxide, any of these detections would give us a direct inventory of what this object is made of, a chemical whisper from another star system carried into our own. Meanwhile, Earth's global network of observatories, both professional and amateur, will not let the moment pass. Telescopes coordinated through the Minor Planet Center and the International Astronomical Union will monitor brightness changes, tail evolution, and spectroscopic shifts. Amateur astronomers, with backyard CCDs and visual estimates, will provide the continuous watch that large observatories cannot sustain. Their nightly records may prove essential in correlating sudden changes in the comet's behavior with the arrival of solar storms. We already know what solar tempests can do. In 2007, ESA's stereo satellites filmed a coronal mass ejection slicing through Comet Encke's ion tail, severing it cleanly in a spectacular display of magnetic reconnection. The comet grew a new tail in hours, while the old one drifted into space, a luminous scar left by the violence of plasma physics. If a similar storm strikes 3I Atlas, the consequences will carry even greater weight. Proof of our sun's influence reaching into matter born beneath alien skies. If 3I Atlas experiences a disconnection event like Comet Encke's in 2007, the spectacle would mean more than just a visual marvel. It would be a probe into the fundamental mechanics of magnetic reconnection, our sun's tangled magnetic fields colliding with frozen volatiles born under alien skies. Differences in chemistry between interstellar ices and familiar solar system comets might change everything about the interaction: how easily gases ionize, how efficiently particles couple to magnetic fields, even how violently the tail severs and reforms. In the faint glow of its coma and tails, 3I Atlas could reveal plasma processes that no laboratory on Earth is capable of reproducing. But the questions reach further than space weather. This visitor carries within its ice and dust the isotopic fingerprints of its birth system. Each ratio of carbon, nitrogen, or oxygen isotopes records conditions of stellar nucleosynthesis, clues to whether the gas and dust that built 3I Atlas were enriched by ancient supernovae or sculpted by quieter stellar winds. For the first time, astronomers will be able to perform close-range spectroscopy on interstellar material, not samples returned by spacecraft, but light itself, split into its constituent lines, whispering the chemistry of another star system across billions of years of travel. The trajectory of 3I Atlas tells a story of exposure. It has drifted for perhaps millions of years through interstellar space, bathing in cosmic rays that may have altered its chemistry, fractured its structure, or eroded its surface volatiles. Now, as it plunges through the inner heliosphere during the peak chaos of solar cycle 25, it encounters a radically different environment, one dominated by coronal mass ejections, fluctuating solar winds, and tangled magnetic fields. Its evolution across these stages becomes a natural experiment, charting how matter formed in one star's nursery adapts to the storms of another. Radio astronomy may provide some of the deepest insights. Sensitive receivers can detect faint molecular line emissions that betray internal temperatures, rotation states, and the rhythm of outgassing jets. Networks of dishes linked through very long baseline interferometry could resolve coma structures with astonishing precision, showing whether the nucleus is a single consolidated body or a fragile assemblage of rubble, held together by little more than gravity's tenuous pull. Each observation would peel back another layer of the visitor's identity. The timing could not be better. When Oumuamua flashed through in 2017, we lacked the coordinated observation networks and real-time space weather modeling we now possess. During Borisov's passage in 2019, solar activity was low, muting the sun's influence. But in 2025, 3I Atlas arrives under the watch of an expanded fleet of spacecraft monitoring solar wind density, mapping CME propagation, and providing near-continuous imaging of the sun's restless surface. Ground-based networks, from professional observatories to dedicated amateurs, are ready to integrate their findings into a global campaign. This convergence of technology and timing makes 3I Atlas a laboratory for heliophysics as much as for planetary science. There is also a practical dimension. While 3I Atlas poses no danger to Earth, its trajectory and observability make it a perfect rehearsal for planetary defense. Tracking its orbit, predicting its evolution under solar heating, and measuring its physical properties test the very techniques humanity would need if a hazardous interstellar object were ever discovered on a collision course. Every brightness curve, every tail shift, every spectroscopic line becomes part of an unplanned but invaluable exercise in readiness. The implications stretch even into the domain of life itself. If spectrographs detect complex organic molecules, cyanides, hydrocarbons, or other prebiotic compounds, it would suggest that the chemistry underpinning biology is not confined to our own stellar nursery. Instead, it may be written across the galaxy, carried in icy bodies wandering between stars. Such a finding would not prove that life itself is common, but it would strengthen the idea that the seeds of life are strewn far and wide, waiting for worlds to take them in. And this is only the beginning. The Mars flyby of October 3rd offers the first vantage point, but the story continues. Perihelion on October 29th, when the visitor endures maximum solar heating. Earth's own closest approach on December 19th, when observatories worldwide will aim their instruments for the clearest view yet. Observations will continue into early 2026, tracking every change in brightness, every twist of the tails, every new spectroscopic signal as the object recedes into darkness. The convergence is remarkable. An interstellar visitor, a solar maximum, advanced monitoring systems, and an international campaign of professional and amateur observers working in unison. The stage is set for discoveries that could redefine our understanding of how stars and their debris interact across the gulf of interstellar space. For scientists, the promise is not just knowledge about a single object, but answers to questions about how stellar systems connect, how matter evolves between the stars, and how our own sun imprints its signature on visitors from beyond. The calendar ahead does not simply mark time, it promises revelation. Part 13, Looking Forward, October and Beyond Circle. October 3rd, October 21st, October 29th. Mark them carefully, and underline December 19th in bold. These dates do not simply belong to calendars. They represent milestones in humanity's attempt to understand visitors from beyond the stars, the influence of our restless sun, and the fragile neighborhood of space that envelopes our planet. What happens across these weeks may answer questions that astronomers have asked for centuries. How do alien ices behave under the heat of a new star? How does space weather sculpt material from other stellar nurseries? And what stories do comets tell about our cosmic origins? October 3rd, a blind date with Mars. On October 3rd, 2025, 3I Atlas will pass within 0.19 astronomical units of Mars, roughly 28 million kilometers. For the first time in human history, an interstellar visitor will sweep past a world that hosts orbiters designed to study precisely this kind of body. ESA's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter have already adjusted their schedules, preparing instruments to capture the encounter. The geometry is unique. From Mars, the interstellar wanderer will be seen from an angle Earth cannot provide, allowing simultaneous observations from two vantage points. That parallax may resolve ambiguities that plagued earlier visitors like Oumuamua and Borisov. How large is the nucleus? How active is the coma? How does alien ice respond to the sun's heat? Harvard's Avi Loeb likened the encounter to a blind date with Mars, an apt metaphor for the mixture of anticipation and uncertainty. The high-rise camera aboard Mars Reconnaissance Orbiter should achieve scales of roughly 30 kilometers per pixel. This is far from resolving boulder fields or craters, yet potentially enough to distinguish whether Atlas is dominated by a compact nucleus or surrounded by a diffuse cloud. Expectations must be tempered. Interstellar visitors rarely appear as more than fuzzy points of light. The real treasure will likely be in spectra, brightness curves, and long-duration monitoring that together build a portrait of alien chemistry and behavior. October 2021. A swan in the night. Just weeks later, Earth skies offer another spectacle. On October 20th and 21st, Comet C divided by 2025 R2, SWAN, makes its closest approach at about 0.26, 0.27 AU. The timing is extraordinary. The moon will be new, leaving skies dark, while the annual Orionid meteor shower reaches its peak. The result is a natural stage set for naked eye astronomy. Predictions suggest magnitude 4 to 6 brightness, enough to glimpse without optical aid under pristine skies, though binoculars or small telescopes will reveal far more. Yet comets are fickle. Some blossom spectacularly into luminous tails stretching across constellations. Others disintegrate or stall, disappointing hopeful observers. SWAN is a newcomer, a long-period comet with no historical precedent. It could astonish or fade into mediocrity. Still, the confluence is unmatched. Imagine one evening in late October, meteors flashing through Orion's rising stars, a comet glowing faintly near the horizon, and far across the solar system, an interstellar object threading past Mars, while solar storms ripple through space. Few generations witness so many celestial performances compressed into such narrow time. October 29. Into the furnace. By the end of October, attention swings back to 3I Atlas as it sweeps through perihelion, its closest approach to the Sun, at roughly 1.36 AU. Though farther from the Sun than Earth, this marks the moment of maximum heating. For an object that has slumbered in interstellar night for millions of years, solar radiation now acts like a sudden furnace. Volatiles long frozen may burst into jets, creating tails of dust and ionized gas. The nucleus could brighten dramatically or fracture under thermal stress, or it may remain stubbornly quiescent, defying cometary expectations. Professional observatories around the world are preparing to watch every flare, every spectral line, every morphological change. The question is not whether something will happen, but whether the phenomena will align with familiar cometary patterns or announce themselves as uniquely interstellar. December 19. Closer than Mars. The year's final act arrives on December 19th, when 3I Atlas passes at 1.8 AU from Earth, about 270 million kilometers. This is closer than Mars at its farthest, and it ensures months of excellent visibility for both professional instruments and amateur telescopes. Unlike Oumuamua, which raced away before observers could coordinate, Atlas lingers. Its trajectory, brightness, and volatile activity can be monitored through early 2026, giving science time to do what it does best: repeat, compare, and refine. Even modest telescopes will track its coma and tail as they evolve under fluctuating solar conditions. For planetary defense specialists, this is a rehearsal in tracking non-solar system objects with precision. For astrobiologists, each spectroscopic signature is a clue about the chemistry of worlds far beyond our Sunday. And for amateur astronomers, it is a chance to follow, night after night, the journey of a genuine interstellar visitor. Such events inevitably attract headlines, promising dazzling sights visible to the naked eye. Reality is subtler. Most likely, Atlas will appear as a dim star-like point, slowly shifting against the background constellations. Its coma and tail may be best appreciated through long exposure imaging rather than casual stargazing. The scientific payoff, however, lies less in spectacle than in data. Isotopic ratios, volatile abundances, and the comet's response to solar weather. These results may not stir the public imagination like photographs of glowing arcs, but they carry the potential to reshape how we think about interstellar chemistry. Meanwhile, the Sun itself refuses to stay quiet. Solar cycle 25 remains at maximum, and late September through October represents the Russell-McFerran window when geomagnetic coupling favors intense storms. Auroras may flare across high latitudes, power grids may face elevated risk, and spacecraft operators will remain on alert. The storms that buffet Earth also sweep across 3I Atlas, giving scientists a laboratory to study how solar violence shapes alien material. Taken together, these months form more than a sequence of dates. They are a compressed drama of celestial forces, interstellar ice, solar fire, cometary dust, and terrestrial observers bound by curiosity. October 3rd brings a rendezvous with Mars. October 21st offers a comet and meteor show. October 29th pushes an interstellar visitor into the furnace of perihelion. December 19th draws it closer to Earth than Mars at its farthest. Individually, each event is remarkable. Together, they form a symphony of coincidence, a reminder that the universe's rhythms sometimes align in ways that feel almost scripted. For scientists, it is a chance to learn. For the rest of us, it is an invitation. Step outside, look upward, and remember that our skies still hold surprises. NOAA's Space Weather Prediction Center continues its round-the-clock watch, using fleets of satellites and global observatories to track every pulse and flare from our Sunday. At the heart of its operations, the Enlil model projects the motion of coronal mass ejections as they surge through the heliosphere, forecasting when these billion-ton storms might buffet Earth's magnetosphere, graze Mars, or even thread through the trajectory of 3I Atlas. For aurora photographers and space weather enthusiasts, the alerts matter. G-scale geomagnetic storms, scale solar radiation surges, and R-scale radio blackouts. These bulletins signal not only technological risk, but also the chance to see shimmering curtains of aurora far below their usual polar latitudes. With solar maximum conditions overlapping the geometric alignments of the equinox, October and November stand as prime months for storms of both plasma and light. While the skies dance, the ground beneath Venezuela remains unsettled. Aftershock sequences continue to ripple through Zulia State following the magnitude 6.2 and 6, three shocks that tore the crust apart in late September. Seismological agencies monitor every tremor, yet the tools of modern science cannot predict when or whether larger ruptures might follow in the same region. The Caribbean, South American plate boundary ensures that earthquakes will return, irregularly but inevitably, across geological time. For now, safety depends less on speculative links to space weather than on practical measures. Strong building codes, tested emergency systems, and resilient public awareness. Far beyond Earth, another pair of stories continues to unfold in the constellations. V1935 Centauri and V7994 Sagittari, the twin novae that erupted into naked-eye brilliance, are now fading along predictable arcs. Their declines still pulse with drama. Astronomers, both professional and amateur, measure brightness night after night, while spectrographs dissect the chemical light of their ejecta. Coordinated through the American Association of Variable Star Observers, thousands of individual data points merge into a coherent chronicle of stellar violence. Meanwhile, high-energy observatories like Fermi and Swift capture gamma-ray signatures that reveal shockwaves accelerating particles to near-relativistic speeds. In the coming months, these stars may darken unexpectedly, veiled by dust grains condensing from their own debris, before brightening again as radiation clears the haze. Each dip, each flicker, becomes another piece in the evolving physics of nova explosions. Against this background of plasma storms, tectonic stress, and stellar death, the human task is one of interpretation. How do we separate solid observation from alluring speculation? Each phenomenon, whether the path of 3-1 Atlas, the aftershocks in Venezuela, the flickering novae, or the restless sun, follows well-established physical laws. They operate independently, without hidden strings connecting them across the void. And yet, the way they converged in late September remains worth documenting. Rarely do such different forces of nature announce themselves on such compressed timescales. Whether that clustering is coincidence, subtle connection, or simply the inevitable rhythm of a restless universe remains uncertain. For audiences, the message is twofold. Enjoy the spectacle, but seek truth from reliable sources. NASA and ESA publish updated mission data. The Minor Planet Center coordinates interstellar and cometary observations. The U.S. Geological Survey and Venezuelan agencies track seismic risks. NOAA's Space Weather Prediction Center provides authoritative forecasts of geomagnetic storms. Together, these institutions form the backbone of trustworthy information, an antidote to sensational headlines and unfounded rumors. Yet this is not a passive era. Ordinary observers can participate directly. Amateur comet photography, nova brightness estimates, aurora logs, even earthquake reports, through local networks, all feed into collective databases. Citizen science, once marginal, now stands as a vital complement to professional campaigns. The night sky and the trembling earth are no longer the exclusive domain of specialists. They are shared theaters where curiosity itself becomes a tool of research. Still, the question lingers in the background. Does the clustering mean something more? To many, the sequence feels uncanny: stars exploding, faults rupturing, storms bursting from the sun, and an interstellar traveler threading through it all. Perhaps the strangeness lies not in hidden causation, but in overlapping timescales. Stellar evolution usually plays out across millennia. Plate tectonics unfolds across centuries. Solar activity peaks every 11 years. Interstellar visitors sweep by only once in generations. That these clocks briefly struck together within weeks is extraordinary, not because physics demands it, but because human lifespans are too short to expect such alignments often. The story will not end with October. Data from Mars orbiters, perihelion observations, and months of continued tracking will feed analysis for years to come. Scientists will work backwards from the records, testing what truly happened rather than indulging what might have been. The verdict may find no hidden ties between earthquakes and solar storms, no cosmic choreography linking novae to comet tails, or it may uncover subtler patterns, faint correlations, or previously unknown interactions. Either way, the distinction between what is observed, what is hypothesized, and what is known will remain central. In the end, what we can assert with certainty is that we have lived through a convergence of stories on scales that humble and inspire. Twin novae flaring across the galaxy, earthquakes shaking Venezuelan cities, auroras spreading under solar storms, an interstellar visitor offering itself to our instruments. None of these alone is unprecedented, but together they remind us of the universe's restless creativity. The conclusion does not require cosmic conspiracy. The true marvel is that we live in an age capable of witnessing, recording, and sharing such events across the globe. For the first time in Earth's history, a civilization can watch interstellar ice vaporize under a new star, measure gamma rays from exploding suns, trace stress across fault lines, and forecast magnetic storms all within the same season. This perspective, denied to every culture before us, is itself a wonder worth celebrating.